Before we begin, take one more slow breath. Let your shoulders drop just a little further away from your ears. Feel the weight of your head settling into the pillow, heavy and safe. There is nothing you need to do right now. There is nowhere you need to be. You do not need to remember anything, and you do not need to picture anything perfectly. This is just a story, a long and gentle one, and you are allowed to let it wash over you like warm water. If you drift away before the end, that is exactly as it should be. If you wake again and the story is still going, you have not missed anything important. Everything that matters will circle back around, soft and slow. This story is about everything, not just the room you are in, or the town outside your window, or the country beyond that, or even the planet itself. This story is about the whole universe, from the very first flicker of its beginning, all the way to a time so far from now that the numbers lose their grip on the mind. It is a long story, the longest story there is, but we are going to take it one small step at a time. You do not have to hold the whole thing in your head at once. No one can. Instead, just let each moment arrive when it arrives, and let each moment go when the next one comes. That is all the universe ever does, after all. One moment, then the next, then the next. For billions and billions of years, that is all that has ever happened. So let us begin at the very edge of what we can say. Let us begin with a number, not because you need to memorize it, but because it is something calm to rest your attention on, like a smooth stone in your hand. The universe, as far as we can tell, is about 13,800,000,000 years old. 13,800,000,000. That is a very large number, so large that it is hard to feel what it means. But do not worry about feeling it. Just let the words sit in the air. 13 billion years, 800 million more. If you stacked up 13,800,000,000 individual years, one on top of the other, the pile would stretch so far that your mind would simply let go of it. And that letting go is welcome here. That is the feeling we are looking for. A gentle release of the need to grasp. 13,800,000,000 years. That is how long the story has been running so far. Not forever. The universe has not always been here. It had a beginning, a real one, a moment when everything we know started to unfold. But here is something important, something honest. The very first instant of that unfolding, the tiniest sliver of the tiniest fraction of a second, is still a place where our understanding runs out. We do not yet know how to describe that first flicker. We do not have the words, and we do not have the equations. And that is all right. Not knowing is not a problem to be solved right now. It is just a quiet fact, a peaceful gap at the very edge of the story. Every good story has a little mystery at its heart. This one has its mystery right at the very beginning. What we can say, what we have pieced together slowly and carefully over many generations of patient looking and thinking, is that the universe began in a state we call the Big Bang. That name can be a little misleading, so let us take a moment to unwrap it. When you hear the word bang, you probably think of an explosion, a bomb going off, something bursting outward into empty space from a single point. That is a very natural picture, but it is not quite the right one. The Big Bang was not an explosion in space. It was the beginning of space itself. It was the beginning of time itself. Everywhere, all at once, started stretching outward from a state that was unimaginably hot and unimaginably dense. Not a single point in a pre-existing room, but the whole building, the whole city, the whole cosmos, all of it beginning to expand from a condition we cannot yet fully describe. Picture, if you like, a loaf of raisin bread rising in the oven. The dough is space, and the raisins are the bits of matter that will one day become stars and galaxies. As the dough rises, every raisin moves away from every other raisin. There is no center raisin that all the others are fleeing from. From the point of view of any single raisin, all the other raisins are getting farther away. That is how the stretching of the universe works. Space itself is what is growing, carrying everything along with it. The Big Bang is the moment the dough first began to rise. What was there before the dough existed? What was there before the oven was turned on? Those are questions that our current understanding cannot answer. Before the Big Bang might not even be a meaningful phrase, because time itself, the steady tick-tock that we measure with clocks and calendars and the beating of our own hearts, seems to have begun right there, at that first moment. The question, what happened before time began, may be like asking, what is north of the North Pole? It is a perfectly sensible string of words, but it does not point to anything real. And that is all right too. We can leave that question hanging, soft and unanswered, like a note that never quite resolves. So the universe began. All of space, all of what would one day become this room, this bed, the air you are breathing, the thoughts drifting through your mind, all of it was compressed into a state so hot and so dense that our everyday words fall apart when we try to describe it. But we do not need to describe it in detail right now. We just need to know that it began, the story started, and from that very first moment, the universe has been stretching, cooling, and unfolding into the shape we see today. 13,800,000,000 years of unfolding. That is the whole journey, laid out end to end. Now, here is the invitation. Do not try to picture the whole thing at once. Do not try to hold 13 billion years in your head like a single object. The mind does not work that way, and trying will only make you tense. Instead, just follow one moment after another, like walking slowly down a long, gentle path in the dark, with only the next step visible. We are going to walk that path together, one soft footfall at a time. We will begin before there was light, before there were stars, before there were even atoms. We will start in a time so early that the universe was still a hot, thick soup of particles, a place no eye could ever see, because there were no eyes, no bodies, no planets to stand on. And we will move forward from there, slowly, through the first cooling, through the first atoms, through the long dark ages when the universe was quiet and still, through the first stars switching on like tiny lamps in a vast night, through the gathering of galaxies, through the birth of our own sun and our own earth, all the way to the present moment, and then beyond. Beyond, into the far future, into a time so distant that even the slowest burning stars will have gone out, and the universe will become a cold, dark, quiet place, a place of stillness, a place of rest. That may sound sad, but it is not meant to be sad. It is just the shape of the story. Every story has a beginning, a middle, and an end. The end of this story is not a crash or a bang or a catastrophe. It is a long, slow fading, a quieting down, a final exhale. And there is something deeply peaceful about that. Something that rhymes with the feeling of your own breathing slowing, your own thoughts quieting, your own body settling into sleep. The universe, in its own way, will one day go to sleep too, and that is all right. But that is a long, long way off. For now, we are at the beginning, the very beginning. And the first thing that happened, the first thing we can talk about with any confidence, is that the universe stretched. Not slowly, not gently, but in an enormous burst of expansion that took almost no time at all. That is where we will go next. Not yet, though. For now, just rest with the number. 13,800,000,000 years. A long, long story. A story that is still going. A story that you are a part of, right now, even as you lie here in the dark, even as your breathing slows, even as your eyelids grow heavy. You are part of this story. You are made of the same stuff, shaped by the same laws, carried along by the same unfolding. There is no rush. The story will still be here when you wake. The universe will still be here, doing what it has always done, one moment after another, patient and slow. So let yourself be heavy. Let yourself be still. The story is in no hurry, and neither are you. Breathe in, and know that the air you are breathing was made inside stars that lived and died long before the earth was born. Breathe out, and know that the warmth of your breath mingles with the warmth of a universe that began hot and has been cooling ever since. You are not separate from this story. You are the story, still being told. And right now, the story is very simple. A person, lying in the dark, listening. A voice, speaking softly, one word after another. A universe, 13,800,000,000 years old, holding it all. There is nothing to figure out. There is nothing to solve. Just this, just here, just now. Drift, if you want to. The story will be here, waiting, whenever you are ready for the next step. And so, if you are still here, still drifting at the edge of wakefulness, let us take the next step, a small one, a gentle one. We are going to move back to the very beginning of the story, the very first page, the very first word, or rather, to the moment just before the first word, when the page was still blank and the ink had not yet touched the paper. That is where this part of the story lives, in a space that is hard to talk about, and even harder to picture, and that is perfectly fine. We are not here to picture it clearly. We are here to sit with the quiet of it, the wide open stillness of not quite knowing. The universe, as we have said, is about 13,800,000,000 years old. That is a real number, a number we have measured with careful instruments and patient observation. But that number only takes us back so far. It takes us back to a moment when the universe was already a tiny, hot, dense thing, already beginning to stretch and cool. What about the moment before that? What about the very first tick of the clock, the very first heartbeat of existence? That is where our knowledge, for now, comes to a gentle stop, and that stop is not a failure, it is not a cliffhanger, and it is not a problem to be solved. It is simply the edge of the map. Every map has an edge. Every story has a place where the teller must say, honestly and quietly, I do not know what happened here, not yet. The very first fraction of a moment, a sliver of time so small that our everyday words for speed and brevity cannot touch it, is not something that our current physics can describe. When we try to write the equations for that first instant, the numbers turn strange. They become infinite, or they stop making sense altogether. The laws of nature as we understand them, the same laws that describe the orbits of planets and the glow of distant stars, seem to have been different back then, or perhaps not yet fully formed. We are missing a piece of the story, a crucial piece right at the very start, and the honest truth is that we may never be able to describe that first instant with any certainty. It may always remain a quiet mystery, a soft blank space at the beginning of everything, and that is all right. The universe does not owe us a full explanation. It gives us what it gives us, and we are allowed to accept the mystery without wrestling with it. So let us not wrestle. Let us instead acknowledge, with a kind of peaceful humility, that the very first moment of the cosmos is still hidden from us. What we can talk about, what we can lean into, is what happened immediately after. Not the first zero, the first tiny step away from zero. When the universe was already real, already a thing, already beginning its long, slow journey toward the night sky we see today. And that moment, that first describable moment, goes by a name you have probably heard before. It is called the Big Bang. Now let us take that name apart very gently, because it is a name that can mislead without meaning to. When we say bang, we think of a firecracker, a thunderclap, a sudden burst of noise and light in the middle of an otherwise quiet day. But the Big Bang was not like that. It was not an explosion that happened somewhere. It was not a blast that went off at a particular place inside a larger, pre-existing room. There was no room. There was no larger space for it to explode into. The Big Bang was the beginning of space itself, and the beginning of time itself. Everywhere that exists now, every point in this vast, dark, star-filled universe, was once packed together in a state of almost unbelievable heat and density. And then, instead of exploding outward into something, it began to stretch. The space between things began to grow. The fabric of reality itself started to expand, carrying everything along with it. That is the Big Bang. Not a bang in the dark, but the dark itself coming into being and beginning to stretch. Think of it this way, if a thought helps. Imagine you are standing on a quiet beach at night, and the tide is coming in. The water does not arrive all at once in a crashing wave. It seeps forward, inch by inch, covering more and more of the sand. The water itself is not coming from some central spout. It is rising everywhere at once, spreading across the whole shore. The Big Bang is a little like that, except instead of water covering sand, it was space itself covering, well, not covering anything, creating the very idea of where, creating the very idea of when. Before the Big Bang, as far as our current understanding can say, there was no where and no when. There was no before. That phrase, before the Big Bang, is one we need to handle with care. It feels like a natural question. What came before the beginning? What happened earlier than the earliest moment? But those questions may not actually mean anything. They may be like asking what is north of the North Pole. You can stand at the North Pole, the very top of the world, and you can point in any direction, and every direction is south. There is no north left to point at. The concept of north simply stops applying. In a similar way, the concept of before may simply stop applying when we reach the beginning of time. Time itself seems to have begun at the Big Bang. The clock started ticking at that first moment. To ask what happened before time began may be a question that our minds can form, but that reality does not answer, because the question itself assumes a before that did not exist. This is not a trick. It is not a riddle meant to frustrate you. It is simply the honest, calm truth of what we currently understand. The Big Bang is the horizon of our knowledge, the furthest back we can see. And what lies beyond that horizon, if anything, is not something we can speak about with confidence. Some ideas suggest that our universe might have emerged from something else, some earlier state, some deeper reality. But these ideas are, for now, just ideas. They are not yet supported by evidence, and they may never be. So we treat them as what they are: possibilities, quiet guesses, thoughts drifting across the mind of science. We do not need to settle on one. We can leave them all hanging, soft and unresolved, like distant clouds on a still afternoon. So here we are, at the very edge of the describable. The universe has just begun. It is smaller than a grain of sand, smaller than an atom, smaller than anything we have words for. It is so hot that the idea of heat itself barely captures it. It is so dense that the idea of density folds under the weight, and it is beginning to stretch. In the next part of the story, we will talk about that stretching, that first great outward rush. But for now, let us just stay here, in this quiet space of not knowing. Let us make ourselves comfortable with the mystery, because the mystery is not an enemy. It is not a wall we have to break through. It is more like the soft darkness of the room you are lying in right now. You cannot see every corner of it. You cannot map every shadow, but you know it is there, holding you, surrounding you, asking nothing of you. The beginning of the universe is like that. A soft darkness, a quiet edge, a place where our words and our numbers gently fall asleep, and what remains is just the simple fact that something is rather than nothing. That is the deepest part of the story, the part we can only approach, never fully grasp, and that is exactly as it should be. A story that gave up all its secrets would be a story with no more life in it. The not knowing is part of the life. The not knowing is part of the calm. So take a breath in this quiet space. Feel the weight of your own body, the slow rise and fall of your chest. Your own existence, right now, is connected to that first moment. The atoms in your body, the energy in your cells, the thoughts in your mind, all trace their lineage back to that hot, dense beginning. You are not separate from the Big Bang. You are the Big Bang, still echoing, still unfolding, still cooling, 13,800,000,000 years later. The mystery that sits at the heart of the cosmos sits at the heart of you too, and you do not need to solve it. You do not need to explain it. You just need to rest with it, the way you rest with your own breathing. Let it be there, unknown and unknowable, and let that be peaceful. Before there was a before. Before there was a here. Before there was a now. That is where we are standing, at the edge of the story, looking out into a quiet that we cannot describe. And from this quiet, something began to stretch, something began to grow. The first real event in the history of everything was about to unfold, but not yet. Not quite yet, for now just the quiet, just the edge, just the soft, honest admission that we do not know what started it all, and we do not need to know to feel the wonder of it. The wonder is in the not knowing. The wonder is in the simple fact that there is a story at all, and that we are part of it. Let your eyes stay closed. Let your breathing stay slow. The story is still here, still moving, still patient. In a little while, we will take the next step. We will move from the quiet edge into the first great movement, the first stretching, the first unfolding. But that will come when it comes. There is no hurry. The universe has been waiting 13,800,000,000 years to tell this story. It can wait a little longer, and so can you. Rest here, in the mystery, for as long as you need. The next words will be here when you are ready for them. If you are ready, we can take another step, a very small step in terms of time, but a very large step in terms of what happened. We are going to move from the quiet edge of the mystery, the place where our understanding fades into softness, and into the first real event that we can describe with any confidence. This event has a name, a word you may have heard before. It is called inflation. Not the kind of inflation that has to do with money and prices, but something far older and far more powerful. Cosmic inflation. The stretching, the great unfurling. Let us begin by being honest again, the way we have been all along. Inflation is a theory. It is a very well-supported theory, one that fits the evidence we have gathered in many satisfying ways, but its deepest cause is still unknown. We do not know what started it, and we do not know what stopped it. We have ideas, of course. There are always ideas. But the honest truth is that the engine behind inflation, the reason it happened at all, remains one of the great open questions in the story of the universe. And that is perfectly all right. We can talk about what we think happened without knowing every last detail. We can describe the stretching without knowing exactly what did the stretching. The not knowing is not a wound, it is just an open door. So, picture, if you can, the universe just after the Big Bang. Not at the very first instant, which we have already said is beyond our reach, but a tiny, tiny fraction of a second later. The universe is still smaller than anything you can imagine. It is still hotter than any heat we have words for, and it is dense, packed with energy, a kind of energy that we do not encounter in our everyday lives. And then, for reasons we do not fully understand, this tiny, hot, dense universe began to stretch. Not gently, not slowly. It stretched at a speed that makes the word fast seem slow. It stretched so quickly, and so dramatically, that in a sliver of time far shorter than a single heartbeat, the universe grew from something far smaller than an atom to something about the size of a grapefruit, or perhaps a basketball, or perhaps much larger still. The exact numbers are not what matters here. What matters is the scale of the change. In a time so short that the human mind cannot really hold it, the universe grew by an enormous factor. It did not just double in size. It did not just triple. It expanded by a factor that we have to write with many, many zeros. This was not an explosion of matter into space. This was space itself, the very fabric of reality, stretching at a rate that far exceeded the speed of light. Now, that phrase, faster than the speed of light, can sound like it breaks the rules. And in a way, it would if we were talking about objects moving through space. Nothing can move through space faster than light. That is one of the firm rules of the universe as we understand it. But inflation was not about things moving through space. It was about space itself stretching. And the stretching of space is not limited by the speed of light in the same way. Space can stretch as fast as it needs to, and in that first tiny fraction of a second, it stretched very, very fast indeed. The timescale we are talking about here is so small that it almost does not qualify as time in the normal sense. If you try to picture it, your mind will probably rebel. That is normal. That is expected. We are talking about a period that lasted something like a billionth of a billionth of a billionth of a second, or even shorter. These are not numbers you need to hold on to. They are not numbers anyone needs to hold on to. They are just markers, signposts, indicating that what happened so quickly that the word quickly does not begin to cover it. It was not a blink of an eye. It was not a flash. It was a span of time so brief that our normal words for brevity fall away into silence. But brief as it was, this period of stretching, this inflation, left marks on the universe that we can still see today. And that is why we think it happened. Not because we have a photograph of it, not because someone wrote it down, but because the universe today looks a certain way, and inflation helps explain why it looks that way. In particular, inflation helps explain why the universe looks so remarkably smooth, so evenly spread out, in every direction we look. Let us think about that for a moment. When we look out into the night sky with our most powerful instruments, we see galaxies and clusters of galaxies scattered across the darkness. And here is the curious thing. The universe looks roughly the same in every direction, to the north, to the south, to the east, to the west, up, down. Every way we point our telescopes, we see a similar distribution of galaxies, a similar large-scale structure, a similar temperature in the background glow of the cosmos. This is strange when you think about it. The universe is very large. 2 points on opposite sides of the observable sky are so far apart that they have never been in contact with each other. Light has not had time to travel from one to the other in the entire history of the universe. They are causally disconnected, as the phrase goes. They have never had a chance to exchange information, to balance out, to come to an agreement about what temperature they should be. And yet they look remarkably alike. How can two things that have never talked to each other look so similar? This is where inflation comes in, with a simple and elegant answer. Before inflation, before that great stretching, the entire observable universe was packed into a space so tiny that everything was in contact with everything else. Every point could talk to every other point. The whole thing was a single, unified, smooth little patch of reality. And then inflation hit, and it stretched that tiny, smooth patch so enormously, so fast, that the smoothness was preserved across vast distances. The 2 points on opposite sides of the sky today look alike because they used to be neighbors. They used to be right next to each other, in that tiny, hot, dense seed before the stretching began. They were in contact, they balanced out, they came to the same temperature, and then inflation pulled them apart so far that they are now on opposite sides of the visible universe. That is why the universe looks smooth, not because it was designed that way, but because it was stretched that way, from a single, unified beginning. This is a calm and beautiful idea. The smoothness of the cosmos, the even spread of galaxies and background light, is a kind of memory. A memory of a time when everything was touching everything else. A memory of unity, preserved across billions of years. Inflation took that unity and stretched it out, like a soft dough being pulled into a thin sheet. But the unity remained, the connection remained, and we can see it today, every time we look up at a sky that is roughly the same in every direction. Inflation also helps explain another feature of the universe, one that we will touch on later when we talk about galaxies and the large-scale structure of things. The very tiny quantum fluctuations, the microscopic jitters that exist in any physical system, would have been stretched by inflation as well. Those tiny fluctuations became the seeds of everything that later formed. The galaxies, the clusters of galaxies, the vast webs of matter that span the cosmos, all of them trace their origin back to tiny, tiny differences in density that were stretched to cosmic size during inflation. So inflation not only made the universe smooth, it also planted the seeds of its later structure. The smoothness and the structure both come from the same event. That is a quiet kind of elegance, the way a single idea can explain so much. But, as we said at the beginning, the cause of inflation remains unknown. What was the force that drove this enormous stretching? We do not have a clear answer yet. We give it a placeholder name, a kind of tag we can hang on the mystery. Sometimes it is called the inflaton field, a field of energy that briefly dominated the universe and then decayed away. But what that field actually was, what caused it to appear, what caused it to disappear, these are questions that are still being explored. The theory of inflation is well supported by evidence, but the deeper theory behind the theory is still a work in progress. And that is fine. That is how science works. It is a slow, patient process of building one layer of understanding on top of another, always aware that there is more to learn, always honest about the limits of what we currently know. So here we are, in this strange and fleeting moment. The universe has just undergone an almost unimaginable stretching. It has gone from a tiny, hot, dense seed to something vastly larger, all in a sliver of time so thin that it barely exists. And now the stretching is slowing down. Inflation is ending. The energy that drove the stretching is converting into the more familiar forms of energy and matter that will eventually make up stars and planets and galaxies and you. The universe is still hot, still dense, but not as hot as before, not as dense as before. It is beginning to cool, the way a hot cup of tea cools when left on a table. And as it cools, new things become possible. Particles begin to appear. The first building blocks of matter begin to take shape. That is where we will go next. But not yet. For now, let yourself rest in the quiet after the stretching. Imagine the universe, still glowing, still dense, but now expanded, now spread out, now beginning its long, slow journey toward the cool, dark sky we know today. The great stretching is over. The universe has taken its first breath. And there is so much more to come, so many billions of years of unfolding. But there is no rush. The story is still moving, still patient, still waiting for you to be ready. The next words will be here when you are. And so the universe, fresh from its great stretching, continues on its way. It is still very young, only a tiny fraction of a second has passed since the very beginning. But already things are changing, cooling, settling into new forms. We are now entering a period that is, in its own way, just as strange and unfamiliar as the inflation that came before it. This is a universe too hot for matter as we know it. A universe so filled with energy and heat that the very idea of a solid object, or even a single atom, is impossible. There are no rocks here, no grains of sand, no droplets of water. There are no planets, no stars, no galaxies. There are not even any atoms. The universe at this stage is a thick, glowing, churning sea of loose particles, all of them rushing around at tremendous speeds, colliding and separating and colliding again in a dance that has no structure and no rest. Let us try to feel, for a moment, what hot means in this context. Not hot like a summer day. Not hot like the surface of a star, hot beyond anything we have ever experienced or ever could experience. The temperature of the universe at this point is measured in trillions of degrees. Trillions, a number so large that it slides off the mind without catching. At these temperatures, the familiar world of solid, liquid, and gas does not exist. Everything is plasma, a state of matter where the basic building blocks of atoms are all torn apart from one another and swim freely through space. It is a soup, a cosmic soup, and it is everywhere. There is no corner of the universe that is cool. There is no place to hide from the heat. The entire cosmos is a single, continuous, roiling ocean of energy. And what is in this soup? What are the ingredients? At the very smallest scale, the scale that we usually need large machines and complex experiments to study, the universe is filled with particles that we have given names to over the past century or so. The most fundamental of these particles, the ones that cannot be broken down into anything smaller, are called quarks. Quarks are tiny, tiny specks of reality, so small that calling them tiny does not really help. They have no size that we can measure. They are, as far as we can tell, point-like. Mathematical points, with no width, no height, no depth. And yet they are real. They carry charges, they interact with each other, and they are the raw material out of which everything else will eventually be built. But quarks are not loners. They do not like to be alone. In the universe we live in today, quarks are always found bound together in groups of 2 or 3, forming larger particles that we are more familiar with. But in the intense heat of the very early universe, the quarks were free. The heat was so great, the energy so overwhelming, that the bonds that usually hold quarks together could not form. The quarks just rushed around, unbound, unattached, swimming through the cosmic soup alongside other types of particles. This state of matter, this sea of free quarks, is sometimes called a quark-gluon plasma. Gluons are the particles that carry the force that binds quarks together. In our everyday universe, gluons act like tiny springs, snapping quarks into tight groups. But in the heat of the early cosmos, the springs were stretched too far, overwhelmed by the sheer energy of everything. The quarks moved too fast, collided too hard, to ever settle down. This is a difficult thing to picture, and that is perfectly all right. You do not need a clear image in your mind. What matters is the feeling of it, the feeling of immense heat, the feeling of incredible density, the feeling of a universe so crowded with particles that it was like a single, continuous substance, with no empty space at all. There was no darkness. There were no shadows. Light, as we normally think of it, could not travel freely. The universe was so dense, so packed with particles, that any ray of light was immediately absorbed by a particle, then spit out again, then absorbed again, over and over, endlessly. It was like trying to shine a flashlight through a thick fog, except the fog was the entire universe, and it stretched in every direction without end. Light was trapped in a constant game of catch, never getting very far before it was caught again. This meant that if you could somehow stand in this early universe and look around, which of course is impossible in every way, you would not see anything distinct. There would be no objects. There would be no horizons. There would just be a bright, featureless glow in every direction, a soft, overwhelming brightness with no source and no edge. Not a light that illuminates things, but a light that is the thing itself. The universe was its own light, its own heat, its own substance. It was one thing, and that one thing was everything. But the cooling continued. That is the steady thread we can follow through all of this. From the very first moment, the universe has been cooling, and as it cools, new things become possible. Think of water vapor condensing on a cold window. When the air is warm, the water stays as invisible gas. But when the air cools enough, the water gas turns into liquid droplets. Something similar happens in the early universe, though with particles and forces instead of water. As the temperature dropped past certain thresholds, the behavior of the particles changed. They began to slow down. The collisions became less violent, and the quarks, those tiny free specks, finally began to feel the pull of the gluons, the force that binds them together. In a wave of transformation that swept through the entire universe, the free quarks paired up and tripled up, snapping into new, more stable arrangements. Groups of 3 quarks came together to form particles called protons and neutrons. These are particles you may remember from school. They are the building blocks of atomic nuclei, the dense cores at the center of every atom. Protons carry a positive electric charge. Neutrons carry no charge at all. Both of them are heavy, relatively speaking, and stable once formed. The universe was now filled not just with loose quarks, but with these new, larger particles, the first real steps toward the matter we know today. This all happened very quickly. The quark soup era lasted only a tiny fraction of a second, perhaps about 1/1,000,000th of a second after the Big Bang. By the time the universe was a single second old, the protons and neutrons had been formed, and the quarks were no longer free. They were all bound up, tucked away inside their new homes, where they would remain, for the most part, for the rest of cosmic history. The sea of loose quarks was gone, replaced by a sea of protons and neutrons, still hot, still dense, still rushing around, but a little more structured, a little closer to the world we know. And alongside the protons and neutrons, there were other particles too. Electrons, for example. Electrons are much lighter than protons and neutrons, and they carry a negative electric charge. In the early universe, electrons were everywhere, just as numerous as the protons, keeping the overall electric charge of the cosmos balanced at zero. There were also neutrinos, ghostly particles that barely interact with anything at all, slipping through the entire universe as if it were not there. And there was light, still trapped, still bouncing endlessly from particle to particle, unable to travel more than a tiny distance before being absorbed and re-emitted. The universe was still a crowded place. Imagine a room so packed with people that you cannot take a single step without bumping into someone. Now imagine that the people are particles, and the room is the entire universe, and the crowding goes on in every direction, forever. That is what it was like. Light, trying to move through this crowd, could not get anywhere. Every time a photon, which is a particle of light, took a step, it hit an electron or a proton and was scattered in a new direction. The universe was opaque, not because it was dark, but because it was too bright, too thick, too full. Light was there, everywhere, but it could not travel. It could not stream through space the way it does today. It was caught in a perpetual traffic jam, a traffic jam that filled the entire cosmos. This is a good moment to pause and just sit with the sensations of it. The heat, the density, the crowding, the constant motion. The universe at this stage was a place of immense energy and no rest. There were no quiet corners. There were no still points. Everything was moving. Everything was colliding. Everything was hot. And yet, even in this chaos, the seeds of order were being planted. The protons and neutrons were stable. The electrons were stable. The basic pieces were on the board, ready for the next steps. The universe just needed to keep cooling, keep expanding, keep thinning out, until the next threshold could be crossed. And that cooling was happening all the time. With every passing second, the universe doubled in size, or more. The expansion that began with inflation had slowed, but it had not stopped. Space was still stretching, still carrying the particles apart, still lowering the temperature bit by bit. The cosmic soup was thinning. The collisions were becoming less frequent. The particles were getting a little more breathing room. And in that growing space, the next great transformation was being prepared. The formation of the first true elements was just around the corner, just a few minutes away in cosmic time. But those minutes are for the next part of the story. For now, let us stay in this hot, crowded, glowing moment. Let us feel the warmth of it, the pressure of it, the sheer aliveness of a universe filled to the brim with energy and potential. There is no matter here yet, not in the way we normally mean it. There are no chairs, no walls, no air to breathe. But the pieces of matter are here. The protons, the neutrons, the electrons, they are all present, all accounted for, all waiting in the heat. They do not know what they are waiting for. They do not know anything at all. They are just following the laws of physics, the deep, reliable rules that govern heat and motion and charge and mass. And those rules are slowly, patiently, leading them toward the next chapter. Your own body, lying here in the dark, is made of protons and neutrons and electrons that were born in that hot, crowded moment. The particles in your skin, your bones, your breath, all of them trace their lineage back to that first few seconds of existence. They have been through every stage of the cosmic story, unchanged in their essential nature, just rearranged over and over again by the slow work of time. You are, in a very real sense, a collection of particles that have been around since the universe was a single second old. They have traveled for 13,800,000,000 years to be here with you now, in this quiet room, in this quiet moment. That is a thought to rest on, not to analyze, not to solve, just to rest on like a pillow. The particles in you are very old, and they have seen a great deal, and they are perfectly content right now to be still, to be warm, to be here, and so should you be. The next part of the story will come when it comes. For now, just the heat, just the crowding, just the slow, steady cooling that is carrying everything forward. And that slow, steady cooling is what leads us now into the next part of the story. The universe is still very young. Only a few minutes have passed since the very beginning. Think about that for a moment. A few minutes, the time it takes to brew a cup of tea, the time it takes to listen to a single song on the radio. In that short, familiar span of time, the universe is going to accomplish something remarkable. It is going to build the first atomic cores, the first nuclei, the first real elements. And the elements it builds in those few minutes will remain the most common elements in the cosmos for the rest of time. We left off with a universe filled with protons and neutrons, still hot, still dense, but cooling all the while. The protons are the positively charged particles. The neutrons are the ones with no charge at all. Both of them are heavy, by particle standards, and both of them are stable enough to last, but they are not yet bound together. They are still just swimming freely in the cosmic soup, bumping into each other, bouncing apart, never sticking for long. The temperature is still too high for them to hold on to each other. Anytime a proton and a neutron come close, the heat shakes them apart again. They need the universe to cool a little more, to thin out a little more, before they can finally join hands and stay that way. And that is exactly what happens. As the minutes pass, the expansion of the universe continues. Space keeps stretching, the temperature keeps dropping, and somewhere around the time when the universe is about 3 minutes old, give or take, the conditions become just right. The temperature has fallen to a point where protons and neutrons, when they collide, can stick together. Not forever necessarily, but long enough for the next steps to happen. Long enough for the first atomic nuclei to form. This process has a name, a long and technical-sounding name that we do not need to linger on. It is called primordial nucleosynthesis. That word, nucleosynthesis, simply means the making of nuclei, the putting together of protons and neutrons into something larger. And primordial means that it happened right at the beginning, in the earliest days of the universe. Primordial nucleosynthesis, the first cooking of the elements, the original kitchen. Here is how it worked, in the simplest possible terms. A single proton is, by itself, the nucleus of a hydrogen atom. Hydrogen is the simplest element there is. One proton, and later, when the universe is cool enough, one electron circling around it. So as soon as protons formed, the universe already had hydrogen. But it did not have anything else. To get anything more complex, you need to add neutrons to the mix. When a proton and a neutron collide and stick, they form a nucleus called deuterium, which is a heavier form of hydrogen. You might have heard it called heavy water, though the water part comes much, much later. For now, it is just a nucleus, a pairing of one proton and one neutron, held together by the strong nuclear force. Deuterium is the first step, the gateway to everything else. But deuterium is fragile. If the universe is still too hot, the deuterium gets broken apart as soon as it forms. The high-energy light, the photons, smash into it and knock the proton and neutron apart again. So there is a waiting period, a short delay, while the universe cools enough for deuterium to survive. Once deuterium can survive, the floodgates open. The process moves very quickly. Two deuterium nuclei can collide and combine to form a helium nucleus. A helium nucleus is made of 2 protons and 2 neutrons. It is a very stable, very tightly bound little package. And once the conditions are right, the universe starts making helium at a rapid pace. Another route to helium involves deuterium colliding with a free proton or a free neutron, building up step by step. The details of the pathways are not what matter here. What matters is the outcome. In a brief flurry of nuclear activity, lasting only a few minutes, the universe converts a significant fraction of its free protons and neutrons into helium nuclei. This is a fast event. The whole thing, from the first stable deuterium to the final tally of helium, happens in roughly the first 20 minutes of the universe's existence. By the time the universe is 20 minutes old, the era of primordial nucleosynthesis is over. The universe has expanded and cooled so much that the particles are too spread out, too slow-moving, to continue fusing together. The window has closed, the kitchen has shut down, and it will not open again, not in the same way, until the first stars form hundreds of millions of years later. So what did this brief burst of cooking produce? The answer is simple and beautiful. It produced hydrogen, helium, and a tiny, tiny trace of lithium. That is all. 3 elements. Hydrogen is the lightest, just a single proton. Helium is the next, 2 protons and usually 2 neutrons. And lithium, the third element on the periodic table, with 3 protons and some neutrons, was made in very small amounts. The universe, after this first cooking, was composed of about 3/4 hydrogen, about 1/4 helium, and a tiny sprinkle of lithium, something like 1 part in a billion. And that is it. No carbon, no oxygen, no nitrogen, no iron, no gold, no silver, no uranium. None of the heavier elements that make up the world around us today existed yet. They would all have to wait for stars. But the important thing, the thing to hold on to, is that almost all the hydrogen and helium in the universe today was made in that first 20 minutes. Think about that. The hydrogen in the water you drink, the helium in the balloons at a birthday party, if you could somehow gather it all up, the hydrogen in the sun, burning steadily in the sky, the hydrogen in your own body, bound up in the molecules of water and fat and protein. Almost all of it was forged in that brief, hot, furious moment, less than half an hour after time began. The universe made the raw materials for everything else in the time it takes to watch a short film, or to take a slow walk around the block. And those raw materials have been here ever since, cycling through stars and planets and oceans and living things, unchanged in their nuclear essence. This is a calming thought if you let it sit. The building blocks of your own existence are very old and very simple and very stable. The protons in your body have been protons for 13,800,000,000 years. They have not decayed. They have not worn out. They have just been, patiently, through every stage of cosmic history. The hydrogen in you is primordial hydrogen, made in the first few minutes. The helium in the universe, the second most abundant element, is also a relic of that time. When you look up at the sun, you are looking at a ball of mostly primordial hydrogen and primordial helium, gathered together by gravity long after they were made, now burning in a slow fusion fire. But the hydrogen itself, the fuel, is ancient. It predates the sun. It predates the earth. It predates everything we know except the universe itself. Now, this event, this primordial nucleosynthesis, happened very fast, but we do not need to rush through it. We can take our time here, in the retelling. We can sit with the quiet wonder of it, the way you might sit with a cup of warm tea and think about where the water came from. The water came from a tap, and the tap from a pipe, and the pipe from a reservoir, and the reservoir from rain, and the rain from clouds. But the hydrogen in the water goes much further back than any cloud. It goes back to a time before the earth, before the sun, before any star. It goes back to a hot, dense, glowing universe, 3 minutes old, filled with protons and neutrons, finally finding each other in the cooling dark. Let the pace of the story slow down here, to match the deep time we are considering. The 20 minutes of nucleosynthesis were fast, yes, but the meaning of them stretches across billions of years. Every atom of hydrogen you have ever encountered, every drop of water, every puff of hydrogen gas, is a messenger from the first moments of creation. It carries with it the memory of that heat, that density, that brief window when protons and neutrons could come together and make something new. And the helium, the second-born element, is also a messenger. When astronomers look at distant galaxies, they see helium, always about 1/4 of the visible matter. That ratio, that cosmic recipe, was set in those first 20 minutes and has not changed much since. It is one of the great confirmations of the Big Bang theory, this prediction and observation of the primordial helium abundance. The universe still bears the signature of its birth. After helium and the trace of lithium, the cooking stopped. The universe was now a mix of bare nuclei, mostly hydrogen and helium, still too hot for electrons to settle around them. The electrons were still free, still swimming through space, still scattering light in all directions. The universe was still a plasma, still a fog, still opaque. The formation of elements was a crucial step, but it did not change the basic fact that light could not travel freely. That would take much longer, hundreds of thousands of years longer. The universe would need to cool far more before the next great threshold could be crossed. But for now, let us just appreciate what has been accomplished. In a universe that is only 20 minutes old, the basic ingredients of everything have been assembled. The periodic table, the great catalogue of all the kinds of atoms, has been started. Hydrogen with 1 proton, helium with 2, lithium with 3. Everything else, all the heavier elements, all the carbon and oxygen and nitrogen and iron and gold, will come later, cooked inside the furnaces of stars. But the foundation has been laid. The simple elements are here, and they will wait, patiently, for the rest of the story to unfold. You, lying here in the dark, are made partly of that primordial hydrogen. The water in your body, which makes up more than half of your weight, is 2 parts hydrogen to 1 part oxygen. The oxygen came later, from stars, but the hydrogen is original. It has been part of this universe since the 3rd minute of existence. It has been part of countless cycles, countless transformations, countless rearrangements, and now it is part of you, for a little while, in this quiet moment. That is a thought to rest on, not to chase, not to analyze, just to rest on. You are made of ancient stuff, stuff that was forged in the first glow of the universe. And that stuff is perfectly at peace, perfectly content, just being what it is, just being here, just being now. The next part of the story will take us into a longer, slower era. The era after the elements were made, but before the light could travel. A time of waiting, a time of cooling, a time of darkness before the first clear light. But that is for later. For now, let the 20-minute kitchen of the cosmos fade into the background. Let the protons and neutrons settle into their new partnerships. The universe is still expanding, still cooling, still moving forward, but it is in no rush. And neither are you. The story will still be here, warm and steady, when you are ready for the next step. The universe has its elements now. Hydrogen, helium, a trace of lithium. The building blocks are ready, but the universe is still not transparent. It is still not clear. It is still a thick, glowing fog, a place where light cannot travel more than a tiny distance before being grabbed by a particle and thrown in a new direction, and it will stay that way for a long, long time. Not minutes, not hours, not days. We are now entering a period that lasts for roughly 380,000 years. 380,000 years of fog, 380,000 years of waiting. This is the long, quiet stretch before light could travel freely. This is the darkness before the first clear light. Let us sit with that number for a moment. 380,000 years. In the scale of a human life, that is an almost unimaginable span of time. It is longer than our species has existed, longer than the oldest cave paintings, longer than any civilization, any empire, any recorded history. And yet, in the scale of the universe, it is just the first gentle sigh. The universe is still in its infancy, still figuring out what it will become. But infancy for the cosmos is a very long phase indeed. During these 380,000 years, the universe continues to do what it has been doing all along. It expands, it cools, it thins out. The temperature drops from trillions of degrees to billions, to millions, to thousands. The cosmic soup of particles gets less and less crowded. The protons and the helium nuclei, the ones made in the first 20 minutes, are still there. The electrons are still there, free and unattached, swimming through space with their negative charges. And light is still there, countless photons bouncing around, unable to escape the constant traffic of charged particles. The whole universe is still a plasma, a hot ionized gas, where matter and light are tangled together in a single, glowing substance. But something is slowly changing. The temperature is falling, and as it falls, the electrons begin to slow down. They are not rushing around quite so fast anymore. The protons and helium nuclei are also slowing. The whole system is getting calmer, quieter, more settled. And there is a threshold approaching, a particular temperature where something wonderful and transformative will happen. That temperature is around 3,000 degrees. Not millions, not billions. 3,000 degrees. Still very hot by human standards, hotter than any oven, hotter than the surface of many stars. But cool enough, finally, for electrons to do something they have not been able to do since the very beginning. Cool enough for electrons to settle into orbit around atomic nuclei and form the first true atoms. This process has a name. It is called recombination. The name is a little misleading because it suggests that the electrons and nuclei had been combined before, and this was a recombining. But in truth, they had never been combined. This was the first time, the first unions, the first complete atoms. So you might think of it not as recombination, but simply as combination, the moment when matter as we know it finally came into being. Here is what happened in the simplest terms. A typical hydrogen nucleus, which is just a single proton, has a positive electric charge. An electron has a negative electric charge. Opposite charges attract. They have always attracted, ever since the universe cooled enough for these particles to exist. But in the hot, early universe, the electrons were moving too fast to be caught. Every time one came close to a proton, it had so much energy that it just bounced away again. The attraction was there, but the heat overwhelmed it. Now, after hundreds of thousands of years of cooling, the electrons have slowed enough that the attraction can win. When an electron passes near a proton, it can be captured. It can settle into a stable orbit around the nucleus. And once it is settled, once it is bound, it forms a complete, neutral hydrogen atom. The same thing happens with helium nuclei. A helium nucleus has 2 protons and usually 2 neutrons, and it carries a positive charge twice as strong as a hydrogen nucleus. As the universe cools, helium nuclei also begin to capture electrons. First 1, then 2. Forming neutral helium atoms. And just like that, the universe transforms. The plasma state, where nuclei and electrons are all free and separate, gives way to a gas of neutral atoms. The charged particles are gone, tucked away inside their new atomic homes. The universe, for the first time, is filled with true, complete, electrically neutral atoms. This moment, this transition, is one of the most important events in the entire history of the cosmos. Because once the electrons are bound inside atoms, something dramatic happens to light. Remember, light had been trapped all this time because it kept running into free electrons. Free electrons are very good at interacting with light. They absorb photons and scatter them in all directions. But neutral atoms are different. A neutral atom, with its electrons settled into stable orbits, does not interact with light in the same way. It lets light pass through. It is transparent. And so, when recombination happened, when the electrons were finally captured, the universe went from being an opaque, glowing fog to being clear, transparent, open. Light could finally travel. It could stream across space without being constantly absorbed and scattered. The universe became visible. This is a moment we can still see today. The light that was released at the moment of recombination has been traveling through space ever since. It has been traveling for 13,800,000,000 years, and we can detect it. We have built instruments that can pick up this ancient light, this first glow of the transparent universe. It is called the cosmic microwave background. Microwave because over the billions of years, the expansion of the universe has stretched the light, cooled it down, shifted it from visible light into the microwave part of the spectrum. Background because it comes from every direction in the sky. It is the afterglow of the Big Bang, the first light that was ever free to travel, still washing over us from all sides. Think of it this way. When you turn on an old television set and tune it to a channel with no broadcast, some of the static you see, some of the snow on the screen, comes from the cosmic microwave background. It is light from the edge of the visible universe, light that has been traveling since the moment the universe became transparent. It is the oldest light in existence, and it is everywhere. It fills the space between stars and galaxies. It passes through your room right now, though you cannot see it with your eyes. It is a soft, cool whisper of the hot, dense beginning, still echoing after all this time. This is a good moment to pause and let that sink in. The universe has just taken its first real breath. It has gone from a glowing, opaque fog to a clear, dark sky. The fog lifts, and for the first time, there is darkness. Real darkness. Not the darkness of a closed room, but the darkness of deep space, where light can travel for billions of years without hitting anything. And into that darkness, the light of recombination streams outward, in every direction, a soft farewell from the hot, crowded early days. The universe is saying its first goodbye. The plasma era is over. The age of atoms has begun. This is what we might call the universe's first sigh, a long, slow exhale after hundreds of thousands of years of heat and pressure. The universe can finally relax a little. It can finally spread out and become something new. The atoms are here. The light is free. The stage is set for the next great chapter. But that chapter will not begin right away. There is still a long, quiet period ahead. A period with no stars, no galaxies, no sources of light except the fading afterglow of recombination. A period that is sometimes called the cosmic dark ages. And that is where we will go next, but not yet. For now, just rest in this moment of release. The fog has lifted. The light is streaming. The universe is clear and calm and open. Let yourself be clear and calm and open too. The story will continue when you are ready. The fog has lifted. The light from recombination, that first great flash of freedom, has streamed out into the newly transparent universe. And then, gradually, that light fades. The universe continues to expand, continues to cool, and as it does, the wavelength of that ancient light stretches out, shifting from visible light into infrared and then into microwaves, growing fainter and cooler and softer with every passing millennium. The glow does not disappear. It is still with us today, as we have said, the cosmic microwave background. But for the universe itself, at this early stage, the fading of that glow means something profound. It means that the universe is going dark, truly dark. For the first time since the Big Bang, there are no new sources of light being made. The afterglow is receding, and there is nothing yet to replace it. This is the beginning of what is called the cosmic dark ages. It is a long, slow, quiet stretch of time. It lasts for roughly 100 million years. 100 million years of darkness, 100 million years of silence, 100 million years of the universe simply being, without any of the bright, burning objects we are used to seeing when we look up at the night sky. No stars, no galaxies, no planets, no moons, just a vast, expanding ocean of hydrogen and helium gas, with a faint trace of lithium drifting in the dark. Let us sit with that for a moment. 100 million years. It is a number that is hard to hold. In human terms, 100 million years is an abyss of time. The dinosaurs went extinct about 65 million years ago. The first flowers appeared on Earth around 130 million years ago. The first mammals scurried through the undergrowth more than 200 million years ago. All of that history, all of that evolution and change and life and death, fits into a span of time that is roughly comparable to the cosmic dark ages. And yet, during all of those 100 million years, the universe was doing almost nothing that we would recognize as eventful. It was just being. It was waiting. It was a vast, quiet, almost empty room, with the lights turned off, and no one yet arrived. Now, this is not to say that absolutely nothing was happening. It was a quiet time, but not a dead time. There were processes at work, slow and patient and unseen. The universe was filled with matter, mostly hydrogen and helium gas, and this gas was not perfectly smooth. Remember the tiny quantum fluctuations that we mentioned during the era of inflation, those microscopic ripples in the fabric of reality that were stretched to cosmic size by the Great Expansion. Those ripples left their imprint on the matter of the universe. Some regions of space were ever so slightly denser than others, ever so slightly more crowded with atoms. The differences were tiny, just a few parts in 100,000. A patch of space with a little more hydrogen here, a patch with a little less over there. But these tiny differences were enough. They were seeds, seeds of structure, seeds of everything that was to come. And during the Dark Ages, something began to act on those seeds. That something was gravity. Gravity is the most patient force in the universe. It never rushes, it never sleeps. It just pulls, steadily and forever, on every bit of matter that has mass. In the Dark Ages, gravity began its long, slow work. In the regions that were slightly denser than average, the gravitational pull was slightly stronger. That slightly stronger pull drew in more gas from the surrounding regions. That made the dense region even denser, which made its gravity even stronger, which drew in even more gas. It was a slow feedback loop, a gentle snowball rolling down an almost imperceptible hill. Over millions and millions of years, the hydrogen and helium gas began to gather. It began to clump. It began to form vast, diffuse clouds, still dark, still cold, but slowly, patiently, growing denser at their centers. There was no light to see this by. If you could have floated in the Dark Ages universe and looked around with eyes that could perceive anything at all, you would have seen nothing. No pinpricks of starlight, no glowing nebulae, no distant galaxies, just darkness in every direction, a darkness so complete, so total, that it would feel almost solid. You would be surrounded by a universe that was, to your senses, empty, and yet, invisible to any eye, the gas was moving, the gravity was pulling, the seeds of the first stars were quietly germinating in the dark. This is a very peaceful stretch of the story. There are no explosions, there are no dramatic events. There is just the slow, steady work of gravity, sculpting the darkness. And because it is so peaceful, this is a good part of the story to let your mind drift a little. The Dark Ages are a perfect place to rest. The universe itself was resting, in a way, gathering its strength, preparing for the next great chapter. There was no rush then, and there is no rush now. The 100 million years of the Dark Ages passed in a deep, cosmic silence, and we can let our own thoughts pass in a similar way, quietly, slowly, without urgency. Let us imagine what that Dark Ages universe was like. It was cold, not absolutely cold, but cold by cosmic standards. The temperature had dropped to only a few tens of degrees above absolute zero. The gas was thin, spread out across distances that are hard to comprehend. If you took a cubic meter of space in the Dark Ages, you might find only a few atoms of hydrogen in it. The universe was emptier than any vacuum we can create on Earth. And yet, because the universe was enormous, the total amount of gas was immense. Oceans and oceans of hydrogen and helium, stretching on forever, or at least as far as the observable universe reaches, all of it dark, all of it quiet, all of it waiting. The hydrogen atoms themselves were almost completely still. They drifted. They bumped into each other occasionally. They felt the gentle tug of gravity from their neighbors. But they did not glow. They did not burn. They were just there, the raw material of the cosmos, patient and unchanging. If you could hold a single hydrogen atom in your hand, which of course you cannot, you would feel nothing. It would be a tiny, invisible speck, with a single proton at its center and a single electron orbiting around it. And yet, this tiny speck, multiplied by an unimaginable number, was the stuff out of which everything else would be built. All the stars, all the planets, all the living things that would ever exist were at this moment just cold hydrogen gas, drifting in the dark. Sometimes, in the denser clumps, the gas would warm up a little. As gravity pulled the atoms closer together, they would collide more often, and those collisions would generate heat. The densest clumps, the ones that would one day become the first stars, began to glow faintly in the infrared. But it was a very faint glow, nothing like the brilliant light of a true star. It was more like the warmth you feel from a hot cup of tea, a gentle, radiant heat, barely detectable. The universe was still, for all practical purposes, dark. This is a good moment to take a breath. If you are still awake, still listening, let your own breathing match the slow, patient pace of the Dark Ages. There is no need to hurry. The story is not going anywhere. The universe waited 100 million years for the first star to ignite. We can wait a few more minutes before we get there. Let the darkness of the cosmic Dark Ages be a comfort to you. Darkness is not a bad thing. It is not a frightening thing. It is just the absence of light, and in that absence, things can grow. Seeds can germinate. Potential can gather. The Dark Ages were not a time of nothing. They were a time of becoming. Everything that would ever be was quietly, invisibly, coming together in the dark. Think of a field in winter. The ground is bare. The trees are bare. There is no color, no movement, no sign of life. But under the soil, the roots are still alive. The bulbs of next spring's flowers are waiting. The nutrients are cycling. The field is not dead. It is just resting. The cosmic Dark Ages were like that. A universe in winter. A universe waiting for spring. The hydrogen gas was the soil. The gravity was the unseen work of the roots. And the first stars, when they finally ignited, would be the first flowers of the cosmos, the first brilliant burst of light and color in a universe that had known only darkness for 100 million years. But we are not quite there yet. We are still in the quiet, still in the waiting, still in the long, slow, peaceful stretch of the Dark Ages. If you feel yourself drifting towards sleep, this is the perfect moment for it. The story is about to get a little brighter, a little more eventful. The first stars are getting ready to switch on, but they are not switched on yet. For now, there is only the dark, only the quiet, only the slow, patient pull of gravity. Let yourself be pulled too, gently, into rest. The universe waited 100 million years. You can wait a little longer. The stars will still be there when you are ready. And then, after 100 million years of darkness, something changed, something new. The first light in the universe that was not the fading afterglow of the Big Bang, but the light of a new kind of object, began to shine. The first stars were switching on, one by one, then in clusters, then in great waves across the cosmos. The darkness of the cosmic Dark Ages was broken by tiny, brilliant points of light. It was not a sudden flash, not a single dramatic moment that lit up the whole sky. It was a gradual process, spread out over tens of millions of years. But from the perspective of the deep time we have been traveling through, it was the next great chapter. The universe was learning to make light for itself. Let us take a moment to understand what a star actually is. It is a simple concept, really, once you strip it down. A star is a ball of gas, mostly hydrogen gas, that has become so large and so dense that something remarkable happens at its center. The weight of all the gas pressing inward, the force of gravity pulling everything together, creates a core of incredible pressure and heat. And when the pressure and heat become great enough, the hydrogen atoms at the center of the ball begin to fuse together. Two hydrogen nuclei, which are just single protons, are pressed so hard that they overcome their natural repulsion and join. Through a series of steps, they form helium. And in the process, a tiny amount of their mass is converted into energy, light and heat. The star begins to shine. This process is called nuclear fusion. It is the engine of every star. It is what makes the sun shine on a summer afternoon. It is what makes distant stars twinkle in the night sky. A star is, in a very real sense, a controlled nuclear explosion that lasts for millions or billions of years, held together by its own immense gravity. The gravity tries to crush the star inward. The fusion energy pushes outward. The two forces balance each other, and the star finds a stable size and brightness. a steady state that can last for an almost unimaginably long time. As long as there is hydrogen fuel in the core, the star will continue to burn. Now, the first stars that formed in the universe were different from most of the stars we see today. They formed in a universe that was much simpler than our own. There were only hydrogen and helium and a trace of lithium. There were no heavier elements at all, no carbon, no oxygen, no nitrogen, no iron, none of the elements that we find in planets and living things. This simplicity meant that the first stars could grow to sizes that are simply not possible today. Without heavier elements to help the gas cool and fragment, the collapsing clouds of hydrogen and helium tended to form very large, very massive stars. Some of them may have been hundreds of times more massive than our own sun. They were true giants, enormous balls of gas burning with a fierce, blue-white light. These first stars lived fast and died young. A star that is very massive burns through its fuel much more quickly than a smaller star. While our sun has been shining for about 4.5 billion years and will shine for several billion more, some of these first stars may have lived for only a few million years. A few million years, compared to the age of the universe, is like the blink of an eye. They formed, they burned brilliantly, and then they exhausted their fuel and ended their lives in enormous explosions, scattering their newly forged heavy elements into the surrounding space. But we will get to that part of the story in a moment. First, let us just appreciate the simple fact of their existence. The first stars, the first points of light in a universe that had known only darkness for 100 million years. Imagine, if you can, what that first light must have been like. Not that anyone was there to see it, of course. There were no eyes, no planets, no living things anywhere in the universe. But if you could have been there, floating in the dark, you would have seen a single point of light appear where before there was nothing. A tiny, brilliant pinprick. Then another. Then another. Like someone lighting candles in a vast dark hole, one by one, each flame small against the immensity of the darkness, but each one a new presence, a new warmth, a new beginning. Over time, the number of stars grew. The dark ages were ending, not with a bang, but with a slow, steady dawn. These first stars did more than just shine. They began the process of building the heavier elements that the early universe could not produce. Remember, primordial nucleosynthesis, that brief cooking period in the first 20 minutes, only made hydrogen, helium, and a trace of lithium. Everything else, every heavier element on the periodic table, had to be made later, and the first stars were the factories that made them. In the cores of these stars, where the temperatures and pressures were even more extreme than in stars like the Sun, fusion continued beyond helium. Helium nuclei fused to form carbon, carbon fused to form oxygen, oxygen fused to form neon, and so on, building up the periodic table step by step, element by element, all the way up to iron. Iron is a special element. It is the most stable nucleus. Fusing elements lighter than iron releases energy, but fusing elements heavier than iron actually consumes energy. So when a massive star builds up an iron core at its center, the fusion engine that had been powering the star for millions of years suddenly stops producing energy. The core can no longer support itself against the crushing weight of the star. And then, in a very short time, the star collapses. This collapse is the event we call a supernova. A supernova is one of the most energetic events in the universe. In a matter of seconds, the core of the star implodes, and the outer layers are blasted outward into space with a force that is almost beyond comprehension. The explosion is so bright that a single supernova can, for a brief period, outshine an entire galaxy of billions of stars. And in the extreme conditions of that explosion, the universe does something remarkable. It forges elements heavier than iron. All the elements that iron cannot make through normal fusion, elements like silver and gold and platinum and uranium, are created in the furnace of a supernova. The explosion scatters all these newly made elements, along with the carbon and oxygen and nitrogen made during the star's life, far out into space. The star dies, but in dying, it seeds the universe with the building blocks of planets and life. This is a very important part of the story. It connects the first stars directly to us. The carbon atoms that make up the backbone of every organic molecule in your body were forged in the core of a star that lived and died long before the Earth was born. The oxygen you breathe was made in a star. The calcium in your bones, the iron in your blood, the sodium and potassium that allow your nerves to fire, all of it was made in the hearts of stars and scattered across space by supernova explosions. You are, in the most literal sense, made of stardust. The first stars were the beginning of that chain. They were the first alchemists, turning the simple hydrogen and helium of the early universe into the rich, complex mix of elements that would one day make life possible. But let us not rush ahead too quickly. The first stars themselves, these enormous, short-lived giants, are still largely a mystery to us. We have never seen one directly. They existed so early in the universe, and they burned out so quickly that their light is very hard to detect. We think they formed perhaps 200 or 300 million years after the Big Bang, though the exact timing is still a subject of study. We have indirect evidence of their existence. We see the heavy elements they produced in the oldest stars that are still around today. We see the effects of their light on the gas in the early universe. But the first stars themselves, the original points of light, have not yet been directly observed. This is one of those places where our knowledge is still incomplete. We have a good story, a well-supported theory, but the details are still being filled in, and that is all right. The not knowing is part of the piece of it. What we can say with confidence is that at some point in the first few 100 million years after the Big Bang, the universe began to fill with stars. These first stars were massive, hot, and bright. They lived fast, died in enormous explosions, and in the process, they enriched the universe with the heavier elements that would make everything else possible. They were the first link in a chain that stretches from the Big Bang to you, lying here in the dark, listening to these words. The hydrogen in your body was made in the first few minutes after the beginning. The heavier elements in your body were made in stars like these first ones, and in the stars that followed. You are a living, breathing record of the entire history of the cosmos. As more and more stars formed, the universe began to change. The light from the first stars began to heat up the hydrogen gas that still filled most of space. This process is called reionization, a word that describes the way the ultraviolet light from the first stars stripped electrons back off the hydrogen atoms, turning the neutral gas back into a plasma. It was like recombination in reverse, but driven by starlight instead of heat from the Big Bang. Over time, more and more of the universe became ionized, transparent in a new way, filled with the light of stars rather than the fading glow of creation. The Dark Ages were truly over. The universe had entered the Age of Stars, an age that would last for billions and billions of years. So let us rest here, in this moment of first light. The darkness is broken, the stars are shining, the universe is beginning to look, in a very rough sense, like the universe we know today. There is still a long way to go. The first galaxies have not yet formed. Our own sun is still billions of years in the future. But the first stars have switched on, and with them, the cosmos has taken a decisive step toward complexity, toward richness, toward life. The candle has been lit. The darkness is no longer complete, and the light is beautiful. Let yourself rest in that light, gentle and distant and very, very old. The stars are shining. All is well. The story will continue when you are ready. The first stars are shining now, scattered across the universe like seeds of light in a vast, dark field. But a single star, no matter how bright, is a solitary thing. The universe, in its slow and patient way, was not content with solitary lights. Gravity, the same quiet force that pulled the first gas clouds together to make those stars, continued its work on larger scales. It began to gather the stars themselves into larger structures, pulling them together across hundreds of millions of years. The first galaxies were beginning to form. To understand how galaxies came to be, we have to step back and look at the universe on a larger scale. After the first stars appeared, the universe was no longer just a uniform sea of hydrogen and helium. It was a patchwork, a tapestry of light and dark, of dense regions and empty voids. Where the first stars had formed, they burned brightly, and when the most massive of them died in supernova explosions, they scattered heavy elements into the surrounding gas. This enriched gas then cooled and collapsed to form new stars, a second generation, still massive, but perhaps not quite as enormous as the first. These new stars formed in clusters, groups of dozens or hundreds or thousands of stars, all born from the same cloud of gas, all held together by their mutual gravity. These star clusters were the seeds of galaxies. Gravity, always at work, pulled the clusters toward each other. Clusters merged with clusters, forming larger clusters. Gas clouds collided and combined, sparking new waves of star formation. Over hundreds of millions of years, these growing collections of stars and gas began to take on recognizable shapes. They became the first true galaxies, enormous islands of stars, gas, and dust, sailing through the expanding universe. Galaxies come in a few basic shapes, and it is worth taking a moment to describe them in simple terms. Some galaxies are flat, rotating disks with graceful spiral arms winding outward from a bright central bulge. These are called spiral galaxies. Our own Milky Way is a spiral galaxy, a great pinwheel of stars and gas, stretching about 100,000 light-years across. The spiral arms are regions where gas and dust are denser, and where new stars are actively being born. The arms are lit up with the blue-white glow of young, hot stars, making them stand out against the darker space between. Other galaxies are more rounded, more like a three-dimensional ball or a stretched-out football. These are called elliptical galaxies. They tend to be redder in color because they are filled with older, cooler stars, and they contain very little of the gas and dust needed to make new stars. Elliptical galaxies are often found in the centers of galaxy clusters, where many galaxies have come together over time. They can be very large, some of them containing trillions of stars. Still other galaxies have no clear shape at all. They are irregular, messy, asymmetrical. Often, an irregular galaxy is the result of two galaxies colliding and merging, their neat shapes torn apart by the gravitational chaos of the encounter. Over time, these irregular galaxies may settle into more orderly forms, or they may remain as they are, permanent records of a turbulent past. The process of galaxy formation was not a single event. It was not something that happened all at once, a few 100 million years after the Big Bang, and then stopped. Galaxy formation is still happening today. Galaxies grow by merging with other galaxies. The Milky Way, for example, has swallowed up many smaller galaxies over its history. Streams of stars, torn from those smaller galaxies by the Milky Way's gravity, still orbit in the outer reaches of our galaxy, ghostly remnants of past mergers. And in the distant future, the Milky Way is on a course to merge with its nearest large neighbor, the Andromeda Galaxy. The two are moving toward each other at hundreds of thousands of miles per hour, drawn together by gravity. In about 4 billion years, they will collide, and over the course of another billion years or so, they will merge into a single, larger galaxy. This is not a catastrophe. It is just the way the universe works. Galaxies grow by coming together. This merging process is very slow, of course. It takes place over timescales that are almost impossible for the human mind to grasp. Hundreds of millions of years, billions of years. When two galaxies collide, the stars inside them almost never hit each other. The space between stars is so vast that even during a galactic merger, individual stars pass by each other like ships in a very large, very dark ocean. But the gas clouds do collide. They slam into each other, compress, and trigger enormous bursts of star formation. A galaxy merger is often lit up with the light of millions of new stars, all born from the shock of the collision. It is a slow, graceful, beautiful process, if you could watch it from outside, over millions of years. So the universe, as it moved past the first few 100 million years, began to fill with galaxies. Not just a few, not just a few thousand, hundreds of billions of them. Each galaxy an island of stars, each star a potential home for planets, each planet a potential stage for the unfolding of complex chemistry and, perhaps, life. The scale of it is hard to hold in the mind, but we do not need to hold it. We can just let it wash over us. Hundreds of billions of galaxies, each one containing hundreds of billions of stars. The numbers are so large that they become almost meaningless, and that meaninglessness is itself a kind of peace. The universe is vast beyond our ability to comprehend, and that vastness is not a problem to be solved. It is just a fact, a quiet, spacious fact, like the darkness of the night sky. In the centers of most large galaxies, something else was growing. As gas and stars fell inward, driven by gravity, they fed enormous black holes that had formed in the early universe. A black hole is a region of space where gravity is so strong that nothing, not even light, can escape. The black holes at the centers of galaxies grew to become supermassive, containing the mass of millions or even billions of suns. As matter fell into these black holes, it heated up to tremendous temperatures and glowed brightly, sometimes outshining the entire galaxy around it. These glowing regions are called quasars, and they were especially common in the early universe, when galaxies were young and gas was plentiful. Today, many galaxies still have supermassive black holes at their centers, but most of them are quieter, having consumed most of the nearby gas and settled into a more subdued state. The black hole at the center of our own Milky Way, for example, is relatively quiet now, a sleeping giant that occasionally stirs but mostly rests. All of this structure, the galaxies and clusters of galaxies and the great black holes at their centers, can be traced back to those tiny quantum fluctuations that were stretched by inflation in the very first fraction of a second. The universe, in its first moment, contained the seeds of everything that would come after. The slight differences in density, stretched to cosmic size, became the foundation for all the structure we see today. Gravity then worked on those differences for billions of years, sculpting them into the rich, complex universe we inhabit. It is a story of almost unbelievable continuity, a thread that runs from the very beginning to the present moment, unbroken and patient. As the universe aged, the rate of star formation changed. In the early universe, when gas was plentiful and galaxies were young, stars were being born at a furious rate. The cosmos was in a kind of stellar baby boom, churning out new stars by the billions. Over time, as the available gas was used up, the rate of star formation began to slow. Galaxies settled into more stable, less active states. New stars were still being born, but not at the same frantic pace. The universe was maturing, calming down, entering a long, steady middle age. That middle age is where we live today. Our own galaxy, the Milky Way, is a mature spiral galaxy, still forming new stars, but not at the rate it once did. The most intense period of star formation in the universe happened about 10 billion years ago, and it has been slowing ever since. But we are getting ahead of ourselves. We have not yet reached the formation of our own sun and our own Earth. That is still a few billion years away in the story. For now, let us rest in this era of galaxy assembly, this long, gentle period of growth and merging and star formation. The universe is filling up with light. The darkness of the dark ages is a distant memory. The sky, if there were eyes to see it, would be bright with the glow of billions of galaxies, each one a city of stars. The cosmos has moved from simplicity to complexity, from uniformity to structure, from darkness to light. And it has done so slowly, patiently, without any rush. The galaxies are still gathering, still growing, still changing, but the pace is unhurried. The universe has plenty of time. Let your own thoughts settle into that same unhurried pace. The galaxies are turning slowly in the dark, their spiral arms trailing starlight across millions of light years. The black holes at their centers are resting quietly. The gas clouds are drifting. The new stars are flickering to life. The old stars are burning steadily. All of it is happening right now, across the universe, in a billion places at once, and it is all connected. Every galaxy, every star, every planet, every particle, all part of the same long, slow story. The story that began 13,800,000,000 years ago, with a stretching of space and a cooling of heat. The story that continues now, in this quiet room, in this quiet moment. The galaxies are gathered, the stars are shining, all is well. The story will continue when you are ready. And now, after all that cosmic history, after the stretching and the cooling, after the first elements and the first light, after the dark ages and the first stars and the gathering of galaxies, we arrive at a moment that is very close to home. In fact, it is home. We are going to talk about the formation of our own sun, our own Earth, our own neighborhood in this vast, sprawling universe. This is the part of the story where the cosmos, in one small corner of one spiral galaxy, began to shape the conditions that would one day make you possible. Let us set the scene. The universe is about 9 billion years old. 9 billion years have passed since the Big Bang. The Milky Way galaxy has been taking shape for billions of years, gathering stars and gas into its spiral arms, merging with smaller galaxies, settling into the graceful, rotating disk we inhabit today. The galaxy is rich with the heavy elements forged by previous generations of stars. Carbon, oxygen, nitrogen, iron, silicon, magnesium, and many others now drift in the interstellar gas clouds, the raw material for new stars and new planets. The universe is no longer the simple place of hydrogen and helium it once was. It is chemically complex, filled with the ashes of dead stars, ready to build something new. In one of the Milky Way's spiral arms, a particular cloud of gas and dust begins to feel the pull of gravity. This cloud is mostly hydrogen and helium, as all things are, but it is also laced with those heavier elements, the stardust from stars that lived and died long before. The cloud is large, perhaps several light years across. It is cold, only a few tens of degrees above absolute zero, and it is slowly, gently, beginning to collapse. What caused the collapse? Perhaps a nearby supernova sent a shockwave through the cloud, compressing it slightly. Perhaps a passing galaxy tugged on it, or perhaps it was simply the slow, patient work of gravity, finally overcoming the internal pressure of the gas after millions of years of quiet waiting. We do not know the exact trigger, but we know the result. The cloud began to fall in on itself, and as it did, it began to spin. This spinning is a natural consequence of the way gravity works. As the cloud contracted, it spun faster, like an ice skater pulling in her arms. The spinning flattened the cloud into a disk. Most of the material fell toward the center, where it piled up into a dense, hot, growing ball. This ball was the proto-sun, the young sun not yet ignited. Around it, the disk of gas and dust stretched outward, thin and flat, rotating slowly around the central mass. In the center of this disk, the proto-sun grew hotter and denser as more and more material fell onto it. The pressure at its core rose to staggering levels. The temperature climbed into the millions of degrees. And then, at a certain point, the conditions became right for nuclear fusion to begin. The hydrogen at the core began to fuse into helium. The sun switched on. It began to shine. That moment, when the first fusion reaction ignited, marks the true birth of our star. The sun became a star, a ball of glowing plasma, flooding the surrounding disk with light and heat. This happened about 4,600,000,000 years ago. 4,600,000,000. That is a number to rest on. It is the age of our sun and the age of the solar system around it. The universe had already existed for 9 billion years before our sun was born. More than half of cosmic history had already unfolded. The sun is not an ancient star. It is a middle-aged star living in a mature universe, born into a galaxy already rich with the history of previous generations. Around the young sun, the disk of gas and dust began to change. The light and heat from the new star pushed away the lighter gases from the inner regions of the disk. Closer to the sun, it was too hot for ices and light gases to survive. Only rocky, metallic materials could condense and remain solid. Farther out, beyond what we now call the asteroid belt, it was cooler. There, ices could form and the giant planets could grow. The material in the disk was not uniform. It was filled with tiny grains of dust, microscopic particles of rock and metal and ice. These grains, over time, began to stick together. Gentle collisions, driven by the motion of the disk, caused the grains to clump. Small clumps grew into larger clumps. Pebbles became boulders. Boulders became planetesimals, rocky bodies the size of asteroids or small moons, a few miles to a few hundred miles across. These planetesimals were the building blocks of the planets. The process of planet formation was messy and violent by human standards, but slow and patient by cosmic standards. Over tens of millions of years, the planetesimals collided and merged. Larger bodies grew at the expense of smaller ones. Gravity, again, was the sculptor. The largest bodies swept up everything in their orbital paths, clearing their neighborhoods of debris. These became the planets. In the inner solar system, 4 rocky planets formed. Mercury, the smallest, closest to the Sun, a world of extreme temperatures and cratered surfaces. Venus, nearly the size of Earth, but shrouded in a thick, toxic atmosphere that traps heat in a runaway greenhouse effect. Earth, our home, a world of liquid water and a protective atmosphere, sitting in the narrow band where conditions are just right for life as we know it. And Mars, smaller and colder, a desert world with a thin atmosphere, but with evidence of a wetter, warmer past. The Earth formed through countless collisions of smaller rocky bodies. Each collision delivered more material, more mass, more energy. The early Earth was a hellish place by our standards. It was molten, a ball of liquid rock, constantly bombarded by asteroids and comets. The heat from these collisions, combined with the heat from radioactive elements inside the Earth, kept the planet in a churning, molten state for millions of years. Over time, the heavier elements like iron and nickel sank to the center, forming the Earth's dense metallic core. The lighter, rocky materials floated to the surface, forming the mantle and the crust. This process is called differentiation, and it gave the Earth its layered structure. One of the most important events in the Earth's early history was a massive collision with a Mars-sized body. We do not know the exact details, but the evidence suggests that a planetesimal, sometimes called Theia, slammed into the young Earth at an oblique angle. The collision was so enormous that it melted the Earth's surface and blasted a huge amount of material into orbit. That orbiting debris, over time, coalesced to form the Moon. The Moon is, in a very real sense, a piece of the Earth, torn away in a cataclysm and bound to us ever since. Its gentle pull creates the tides, stabilizes our planet's tilt, and has been a silent companion in the night sky for most of Earth's history. After the giant impact, the Earth began to cool. The surface solidified into a thin crust. Volcanoes belched gases into the sky, creating the first atmosphere. Comets, rich in water ice, bombarded the planet, delivering the water that would one day fill the oceans. Over hundreds of millions of years, the Earth transformed from a molten hellscape into a world of rock and water and air, a world ready for the next great chapter, the origin of life. But that is another story, a story that belongs to biology as much as to cosmology. For our purposes, what matters is this: the Earth formed along with the rest of the solar system about 4,600,000,000 years ago, from a collapsing cloud of gas and dust in a spiral arm of the Milky Way. The Sun ignited and began its long, steady burn. The planets took their places in their orbits. The solar system, our home, was born. Let us take a moment to appreciate the gentleness of this story, even though it involved collisions and molten rock and giant impacts. The gentleness is in the timescale. All of this took tens of millions of years. The Earth was not made in a day. It was made over an immense span of time, through countless small steps, each one building on the last. The atoms that make up the Earth, and the atoms that make up you, were forged in stars and scattered by supernovas, then gathered into a cloud, then compressed into a disk, then clumped into planetesimals, then collided into a planet. Every step was slow, every step was patient, every step was part of a chain of events that stretches back to the very beginning. And here you are, lying in the dark, the product of that chain. The calcium in your bones was forged in a star. The iron in your blood was forged in a star. The oxygen you breathe was forged in a star. The hydrogen in your water was made in the first few minutes after the Big Bang. You are a collection of ancient atoms, arranged for a brief moment into a living, breathing, thinking person. And that is a thought to rest on, not a thought to chase or analyze. Just a thought to hold, gently, like a smooth stone in your palm. The sun is still shining. It has been shining for 4,600,000,000 years, and it will shine for several billion more. The Earth is still turning. The moon is still orbiting. The story of our solar system is still unfolding, right now, in this quiet moment, and you are part of it. You are not separate from the cosmos. You are the cosmos, looking at itself, listening to its own story, settling into rest. The next part of the story will take us to the present day, and then beyond, into the far future. But for now, just rest here, in the warmth of the sun's light, in the gentle pull of the Earth's gravity, in the quiet of a planet that has been spinning for billions of years. You are home. The story will continue when you are ready. We have traveled a long way together, from the quiet mystery before the Big Bang, through the great stretching of inflation, through the hot soup of particles, the first elements, the long dark ages, the first stars, the gathering of galaxies, and the birth of our own sun and earth. We have covered more than 13 billion years of history, and now we have arrived at the present moment, the universe as it looks right now, today, in this quiet instant. This is a natural place to pause, to catch our breath, to look around and take stock of where we are before the story turns toward the far future. So let us describe the universe as we currently understand it. Not the universe of the distant past, and not the universe of some far-off future, but the universe that exists right now, all around you, even as you lie here in the dark. It is a universe that is vast beyond easy comprehension, and it contains a great deal that we do not yet fully understand. And that is all right. The not knowing is still part of the story. It always has been. The observable universe, the part of the cosmos that we can see with our telescopes and instruments, is a sphere about 93 billion light-years across. A light-year is the distance that light travels in 1 year, about 6 trillion miles. So the observable universe is something like 560 billion trillion miles from one side to the other. These numbers are so large that they slide right off the mind, and that is fine. We do not need to grasp them. We just need to know that the universe is very, very big. Within this enormous sphere, there are on the order of hundreds of billions of galaxies, perhaps 200 billion, perhaps 2 trillion. The exact count is still a matter of study, but it is a huge number. Each of those galaxies, as we have said, contains hundreds of billions of stars. The total number of stars in the observable universe is something like a 1 followed by 22 zeros, or more. It is a number so large that it might as well be infinite for the purposes of our imagination. And around those stars we are now beginning to understand there are planets. Lots and lots of planets. In the last few decades, we have built instruments that can detect planets around other stars, and what we have found is that planets are not rare. They are common. Most stars, it seems, have planets of some kind. Some of those planets are rocky, like Earth. Some are gaseous, like Jupiter. Some orbit in the habitable zone, where liquid water could exist on their surfaces. We do not yet know if any of them harbor life. That is one of the great open questions, and it is a question we are actively working to answer. But the sheer number of planets in the universe suggests that Earth may not be unique. There may be other worlds, other biospheres, other beings looking up at their own night skies, and wondering about their own place in the cosmos. But there is more to the universe than just stars and planets and galaxies. There are two large components of the universe that we know exist, but whose true nature remains deeply mysterious. These are the parts of the story where we must be especially honest and say, plainly and calmly, that we do not yet fully understand what they are. They are called dark matter and dark energy. The names are a little misleading because they suggest something sinister. They are not sinister. They are just unknown. Dark, in this context, simply means that we cannot see them directly. We know they are there because of the effects they have on the things we can see. Let us begin with dark matter. Dark matter is a kind of matter that does not emit, absorb, or reflect light. It is completely invisible to our telescopes. We know it exists because we can see its gravitational pull on visible matter. The stars in galaxies orbit the centers of their galaxies at speeds that cannot be explained by the gravity of the visible matter alone. There is not enough visible stuff, not enough stars and gas and dust, to hold the galaxies together by gravity. If the visible matter were all there was, the galaxies would fly apart. But they do not fly apart. They hold together. Something else, something invisible, is providing the extra gravity. That something is what we call dark matter. We do not know what dark matter is made of. It is not made of ordinary atoms, the kind we are made of. It is something else, some kind of particle that we have not yet detected directly. There are experiments running right now, deep underground in old mines and in laboratories around the world, trying to catch a dark matter particle as it passes through the Earth. So far, no definite detection has been made. But the evidence from the motions of galaxies is very strong. Dark matter is real. It makes up about 85% of all the matter in the universe. The ordinary matter, the stuff of stars and planets and people, is only about 15% of the total. So most of the matter in the universe is something we cannot see and do not yet understand. That is a humbling thought, and it is a peaceful thought, if you let it be. The universe is bigger and stranger than our current knowledge. There is still mystery. There is still room for discovery. And then there is dark energy. Dark energy is even more mysterious than dark matter. It is not a kind of matter at all. It is something else, something that is causing the expansion of the universe to speed up. We have known since the early 20th century that the universe is expanding. The galaxies are moving away from each other, carried along by the stretching of space. But for a long time, we assumed that this expansion was slowing down. Gravity, after all, pulls things together. The combined gravity of all the matter in the universe should be acting as a brake on the expansion, slowing it down over time. But in the late 1990s, astronomers made a surprising discovery. They were studying distant supernovas, explosions of stars that can be used to measure cosmic distances. And what they found was that the expansion of the universe is not slowing down. It is speeding up. The galaxies are moving away from each other faster and faster as time goes on. Something is pushing them apart, overwhelming the pull of gravity on the largest scales. That something is what we call dark energy. What is dark energy? The honest answer is that we do not know. It is one of the biggest open questions in all of science. One idea is that dark energy is a property of space itself, a kind of energy that is present everywhere, even in empty space, and that this energy produces a repulsive force that pushes space apart. Another idea is that it is a field, something like the inflation field that drove the great stretching in the very early universe, but much weaker and operating now. But these are ideas, not settled facts. The true nature of dark energy remains unknown. And that is all right. It is a mystery, but it is a gentle mystery. It does not threaten us. It does not demand to be solved. It is just there, a deep question at the heart of the cosmos, waiting for future generations of curious minds to explore. Together, dark matter and dark energy make up about 95% of the total content of the universe. Dark energy is about 68%. Dark matter is about 27%. The ordinary matter, the stuff we can see and touch and study, is only about 5%. 5%. The universe we see, the universe of stars and galaxies and planets and people, is just a thin layer of frosting on a much larger, much darker cake. We are living in a universe that is mostly unknown to us, and that is not a cause for alarm. It is a cause for wonder, a quiet, patient wonder. There is so much more to learn. There is so much more to discover. The story is far from over. So here we are, at the present moment. The universe is about 13,800,000,000 years old. It is filled with hundreds of billions of galaxies, each with hundreds of billions of stars. It is expanding, and that expansion is accelerating, driven by a mysterious dark energy that we do not yet understand. It is held together on the scale of galaxies and clusters by a mysterious dark matter that we also do not yet understand. And on one small planet, orbiting one ordinary star, in one spiral arm of one galaxy among hundreds of billions, there are minds that can contemplate all of this. Minds that can ask questions about the beginning and the end. Minds that can tell stories about the cosmos, and listen to those stories in the dark. This is a good place to pause. The story so far has been a story of becoming. From a hot, dense beginning, through the formation of elements and stars and galaxies and planets, to the present moment of complexity and consciousness. But the story does not end here. The universe is still changing. The future stretches out ahead of us, vastly longer than the past. And the next part of the story is a different kind of story. It is not a story of becoming, but a story of fading. The stars, which have been the main characters for most of cosmic history, will not shine forever. The universe is already past its peak of star formation. The long, slow process of running out has already begun. But that is for the next chapter. For now, let us just rest in the present. The universe as it is right now, vast and mysterious and beautiful, filled with questions we have not yet answered. And you, a part of it, here in the quiet. The stars are still shining, the galaxies are still turning. The mystery is still unfolding, and that is enough. The story will continue when you are ready. And now we turn a corner in the story. We have traveled from the very beginning up to the present moment, a journey of 13,800,000,000 years. The universe has been a story of becoming, of light emerging from darkness, of structure emerging from simplicity, of complexity emerging from the patient work of gravity and time. But the story does not end at the present. The future stretches out ahead, and it is vastly longer than the past. The universe is still young, in a sense. The era of stars, which began a few 100,000,000 years after the Big Bang, is still underway. But it will not last forever. The stars are already beginning to run out. This is not a sudden event. It is not a catastrophe. It is a slow, gradual, almost imperceptible change, spread out over timescales that are so large they make the current age of the universe seem like a brief moment. We are talking about trillions of years, thousands of billions of years. The universe is only 13.8 billion years old right now. The star-forming era will last for perhaps 100 trillion years, or even longer. That is 10,000 times the current age of the cosmos. So there is no rush. The stars are not going out tomorrow, or next week, or in a billion years. But they are going out. The process has already begun. Let us understand why. Star formation depends on gas, cold, dense clouds of hydrogen and helium, and the heavier elements that have been built up over generations of stars are the raw material from which new stars are made. In the early universe, gas was everywhere. Galaxies were rich with it. The rate of star formation was very high, peaking around 10 billion years ago. But every time a star forms, it consumes gas. Every time a star dies, if it is massive enough, it blows some gas back into space, but not all of it. Some of the gas is locked up forever in the dead remnants of stars, in white dwarfs and neutron stars and black holes. Over time, the supply of fresh gas in galaxies gets used up. The rate of star formation slows down. This is happening right now, in our own galaxy and in galaxies across the universe. We are past the peak. The great stellar baby boom is over. The universe is entering middle age, and the birth rate of new stars is declining. Think of it like a forest. In the early days, the forest is lush and green, with new trees sprouting everywhere. But as the forest matures, the soil gets depleted. Old trees die and fall, and their nutrients slowly return to the earth, but not all of them. Some are lost. Over time, the forest thins out. New trees still grow, but fewer and fewer each season. The same is true for stars. New stars are still being born. In our own galaxy, about one new star is born every year. But that rate is much lower than it was billions of years ago, and it will continue to decline. As the gas runs out, the most massive stars will be the first to stop forming. Massive stars require enormous amounts of gas to form, and they live very short lives. Once the gas supply dwindles, the conditions for making these giants become rare. The universe will increasingly be populated by smaller, longer-lived stars, and the longest-lived stars of all are called red dwarfs. Red dwarfs are small, cool, dim stars. They are much less massive than our Sun, some of them only a tenth or even a 20th of the Sun's mass. Because they are so small, they burn their fuel very slowly, very, very slowly. A red dwarf can shine for trillions of years. The smallest red dwarfs may last for 10 trillion years or more. That is 1,000 times the current age of the universe. A red dwarf born in the early universe would still be in its infancy today. These stars are the ultimate survivors, the last lights that will remain in the far, far future. Our own Sun is not a red dwarf. It is a medium-sized star, and it will not last for trillions of years. It is about halfway through its life right now. In about 5 billion years, it will exhaust the hydrogen fuel in its core and begin to swell into a red giant. It will grow so large that it will engulf the orbits of Mercury and Venus, and possibly Earth as well. Any life that remains on this planet will long since have been extinguished by the increasing heat. The Sun will then shed its outer layers, creating a beautiful, glowing shell of gas called a planetary nebula. The core that remains will collapse into a white dwarf, a dense, hot ball of carbon and oxygen about the size of the Earth. That white dwarf will slowly cool over billions and billions of years, eventually fading to a cold, dark cinder. But that is just one star. The universe as a whole will continue for a long time after our Sun is gone. As the trillions of years pass, the larger, brighter stars will die off one by one. The night sky, if there were still eyes to see it from some distant planet around a surviving red dwarf, would grow dimmer and redder. The spiral arms of galaxies, once lit up with the blue glow of young stars, would fade to a dull red. The galaxies would become populated mostly by red dwarfs, small and faint, but still shining, still making light. The universe would not be completely dark yet, but it would be a twilight universe, a universe of embers rather than flames. During this era, galaxies will also continue to change in other ways. The merging process that we talked about earlier will continue. Over trillions of years, galaxies will merge with their neighbors, forming larger and larger elliptical galaxies. The stars within these galaxies will interact gravitationally, and some stars will be flung out into intergalactic space, to drift alone in the dark. The remaining gas will be used up or blown out. The galaxies will become what astronomers sometimes call red and dead, filled with old red stars and very little star formation. They will be quiet places, calm places, slowly fading places, and all the while, the universe will continue to expand. Dark energy, that mysterious force we spoke of in the last section, will keep pushing galaxies apart. Galaxies that are not gravitationally bound to each other will move farther and farther away. The observable universe will effectively shrink as distant galaxies slip beyond the cosmic horizon, too far away for their light to ever reach us. If there were astronomers in this far future era, living on a planet around a red dwarf, they would look out with their telescopes and see a much emptier sky than we see today. They might see only their own galaxy, or the merged remnant of several galaxies, surrounded by a vast, dark void. They might have no way of knowing about the Big Bang, or the cosmic expansion, or the existence of other galaxies. The evidence for the true history of the universe would slowly fade away, as surely as the stars themselves. But that is still a very long way off, trillions of years. Let us not rush past the present too quickly. It is important to remember that we are still in the era of stars. The stars are still shining. The sun will rise tomorrow. The universe is still a bright and beautiful place. The running out is a slow, slow process, and we are only at the very beginning of it. There is no cause for sadness here. This is just the shape of the story. Every story has a middle, and every story has an end. The end of the stellar era is not a violent end. It is a gentle fade, a quiet winding down, a slow exhale. Think of a campfire at the end of a long evening. The big logs have burned away, the flames have died down, but the embers still glow, red and warm, casting a soft light over the faces gathered around. The fire is not out yet. It will last for hours, slowly cooling, slowly dimming, but still giving warmth. The stellar era of the universe is like that campfire. The big flames, the massive bright stars, have mostly burned out or are burning out. But the embers, the red dwarfs, will glow for a very long time. Trillions of years. Long enough for unimaginable things to happen. Long enough for new stories to unfold that we cannot predict. We do not know if life will survive into this far future. We do not know if intelligence will persist. We do not know if any civilization, anywhere, will find a way to endure the slow fading of the stars. These are questions that science cannot yet answer. They are open. They are mysteries. And that is all right. The not knowing is part of the peace of the far future. We can let it be what it is, a vast, open question, stretching out into the darkness. For now, let us just rest with the knowledge that the stars are beginning their long, slow goodbye. Not a sad goodbye, not a frantic goodbye, a peaceful, patient goodbye. The universe has given us so much light. It has given us the sun that warms our skin, the stars that fill our night sky with wonder, the elements in our bodies that were forged in stellar furnaces, and it will continue to give light for trillions of years to come. The stars are not in a hurry to leave. They will take their time, and so can we. The story will continue when you are ready. The embers are still glowing. The night is still warm. Rest here, in the long twilight of the cosmos, and let the slow fade carry you gently towards sleep. There is no rush. There is no hurry. The stars are still shining, and they will be for a long, long time. But even the longest-lived stars, the red dwarfs that burn for trillions of years, will eventually run out of fuel. They will dim, one by one, and go out. And when the last star in the universe finally exhausts its hydrogen, when the last fusion reaction sputters to a stop, the universe will enter a new era, an era with no starlight at all, an era of cold, dead stars. This is the era that is sometimes called the degenerate era, a name that refers to the kinds of objects that will dominate the cosmos when all the ordinary stars have gone. The degenerate era will begin roughly 100 trillion years from now, give or take. 100 trillion years. That is a number so large that it barely registers. The universe is only 13.8 billion years old now. 100 trillion years is nearly 10,000 times longer than the entire current age of the universe. All of cosmic history so far, from the Big Bang to the present moment, is just a brief prelude to the long, slow twilight that will follow. The universe will spend most of its life in the degenerate era. The age of stars, the age we live in now, is just a short, bright chapter in a much longer, much darker story. So what will the universe look like in this far future time? The ordinary stars will all be gone. The red dwarfs, the last holdouts, will have burned through their fuel and faded to black. What will remain are the corpses of stars, dead stars, stellar remnants. There are three main kinds of these remnants, and they will be the primary objects populating the universe during the degenerate era. The first kind is called a white dwarf. We mentioned white dwarfs earlier when we talked about the eventual fate of our own sun. A white dwarf is the leftover core of a star that was not massive enough to become a supernova. When a star like the sun exhausts its fuel, it swells into a red giant, then sheds its outer layers, leaving behind a small, dense, incredibly hot core. That core is the white dwarf. It is about the size of the Earth, but it contains the mass of a star. It is made mostly of carbon and oxygen, packed together so tightly that a teaspoon of white dwarf material would weigh many tons. White dwarfs are no longer undergoing fusion. They shine only because they are still hot from their formation. Over time, immense spans of time, they slowly cool. They radiate their heat away into space. A white dwarf will cool from a brilliant blue-white to a dim red, then to an infrared glow, and eventually, after hundreds of billions of years, to a cold, dark, solid ball. A black dwarf. The universe is not yet old enough for any black dwarfs to exist. The oldest white dwarfs are still warm, but in the degenerate era, black dwarfs will be everywhere. The second kind of stellar remnant is called a neutron star. A neutron star is what is left when a star, more massive than the Sun, but not quite massive enough to become a black hole, explodes as a supernova. The core collapses under its own gravity with such force that the protons and electrons are crushed together, merging to form neutrons. The result is an object that is only about 10 or 20 miles across, but contains the mass of a star. A neutron star is unimaginably dense. A teaspoon of neutron star material would weigh about as much as a mountain. Neutron stars are born spinning very fast, sometimes hundreds of times per second, and they have incredibly strong magnetic fields. Over time, they too will cool and fade. They will stop spinning, stop pulsing, and become cold, silent spheres of ultra-dense matter, drifting through the dark. The third kind of stellar remnant is the black hole. Black holes are formed when the most massive stars die. The core collapse is so complete, so total, that nothing can stop it. All the mass falls inward to a single point, a singularity, surrounded by a boundary called the event horizon. Nothing, not even light, can escape from within the event horizon. Black holes are the ultimate dead stars, objects of pure gravity, invisible against the blackness of space. In the degenerate era, black holes will be the largest individual objects left. Some will be the remnants of single stars. Others, the supermassive black holes at the centers of galaxies, will have grown even larger over the eons, having swallowed much of the surrounding matter. During the degenerate era, the universe will be a dark, quiet place. There will be no new starlight. The galaxies, what remains of them, will be collections of white dwarfs, neutron stars, and black holes, slowly orbiting each other in the dark. Occasionally, two stellar remnants will collide or merge, producing a brief flash of energy, a gamma-ray burst or a gravitational wave, but these events will be rare and short-lived. Most of the time, the universe will be silent. The temperature will be close to absolute zero. The cosmic microwave background, the ancient afterglow of the Big Bang, will have been stretched by the expansion of the universe so much that it will be undetectable, lost in the cold. And yet, even in this cold and quiet, the universe will not be completely still. There will be slow, patient processes at work. Black holes, as it turns out, do not last forever. According to a theory proposed by the physicist Stephen Hawking, black holes can slowly lose mass and energy through a process that has come to be called Hawking radiation. This radiation is incredibly faint. For a black hole with the mass of a star, it would take an almost unimaginable amount of time to evaporate completely. We are talking about timescales of 10 to the power of 67 years, or even longer, numbers with dozens of zeros. The human mind cannot truly grasp these spans of time. They are so vast that the entire history of the universe so far, the 13.8 billion years, is like a single heartbeat compared to the age of the universe during the black hole era. But eventually, in this slow, patient way, Even the black holes will evaporate. They will give off their last faint glow and disappear, leaving behind nothing but a thin haze of subatomic particles. And then there is the question of matter itself. The protons that make up the nuclei of atoms, the protons that were forged in the first few minutes after the Big Bang, may not last forever. Some theories of particle physics suggest that protons are not truly stable. They may decay, after an enormously long time, into lighter particles. This has never been observed. It remains an unconfirmed idea, a theoretical possibility. But if protons do decay, then even the white dwarfs and neutron stars and planets and any other ordinary matter will eventually fall apart. The timescale for proton decay, if it happens, is even longer than the timescale for black hole evaporation. We are talking about 10 to the power of 34 years, or even longer. It is a span of time so vast that it makes the black hole era seem brief. If protons decay, then eventually all ordinary matter will dissolve into a thin soup of electrons and neutrinos. The universe will be stripped of all structure. No stars, no planets, no rocks, no atoms. Just a cold, thin, expanding sea of the smallest particles. But let us be honest and calm about this. Proton decay is not a settled fact. It is a possibility, an idea that some theories predict and others do not. We do not know if it will happen. We may never know. The timescales involved are so enormous that they are, for all practical purposes, beyond our reach. And that is all right. The not knowing is part of the peace of the far future. We can describe what might happen without needing to be certain. The story of the universe's end is not a single, definite narrative. It is a collection of possibilities, a branching path of ideas, each one quiet and slow and calm in its own way. What we can say with more confidence is that the degenerate era will be a time of extraordinary stillness. The frantic energy of the early universe, the blazing light of the stellar era, will be distant memories. The universe will be a cold, dark, almost empty place, and yet it will not be a place of chaos or violence. It will be a place of deep, profound peace. The objects that remain will move slowly, cool slowly, fade slowly. The universe will be like an old house at night, its fires burned down to ash, its inhabitants long since retired, settling into a silence that will last for eons beyond counting. Let us sit with that silence for a moment. Let it wash over us. The silence of the degenerate era is not a frightening silence. It is the silence of a snow-covered field in midwinter. It is the silence of a library after hours. It is the silence of a bedroom in the deepest part of the night, when even the house has stopped creaking and the world outside is still. The universe, in its old age, will be a quiet, gentle place. It will have done its work. It will have made its stars and its galaxies and its planets and its life. And then it will rest. It will rest for a very, very long time. And if protons do not decay, if black holes are the final state of matter, then the universe may persist in that cold, quiet state forever. Or it may not. There are other ideas, other possibilities. Some theories suggest that the expansion driven by dark energy may eventually tear everything apart, even atoms and particles, in a scenario sometimes called the Big Rip. Other theories suggest that the universe may eventually stop expanding and collapse again, in a kind of reversed Big Bang. But these are less supported by current evidence. The leading idea, the one that fits the data we have right now, is the one we have been describing: a long, slow cooling, a fading of all light, a gradual thinning into cold and dark. This is the universe of cold, dead stars. It is not a sad universe. It is just a universe that has grown old, the way all things grow old, the way a tree grows old and stands bare in winter, the way a mountain wears down over millions of years to a gentle hill, the way the human body, after a long life, finally settles into its final rest. There is a beauty in this, a quiet, patient beauty. The universe will not rage against the dying of the light. It will simply let the light go, gently, peacefully, with the same slow grace with which it first let the light appear. So rest here, in this far future calm. The last stars have gone out. The white dwarfs and neutron stars are cooling in the dark. The black holes are slowly evaporating. The universe is quiet. It is at peace. And you, a part of it, can be at peace too. The story is not over yet. There is still one more chapter, the long, quiet end. But that is for the next section. For now, just the quiet, just the cold, just the slow, patient waiting of a universe that has all the time in existence, and nothing left to do but rest. And so we come to the final chapter, the long, quiet end. We have traveled together from the very beginning, from the mystery before the Big Bang, through the great stretching of inflation, through the hot soup of particles, the formation of the first elements, the long dark ages, the first stars, the gathering of galaxies, the birth of our own sun and earth, the present moment, the slow fading of the stars, and the cold era of dead remnants. Now we stand at the furthest edge of the story we can tell. The universe has grown old, it has grown cold, it has grown quiet, and we are here, at the end of all things, to see what might finally become of it. Let us begin with honesty, as we have tried to do all along. The true final fate of the universe is not settled science. We do not know, with certainty, how the story ends. We have ideas, theories, possibilities. Some of them are better supported by evidence than others. But the deepest truth is that we are peering into a darkness that our instruments cannot fully penetrate. We are extrapolating from what we know, projecting forward into spans of time that are almost incomprehensibly vast, and so we must hold our conclusions lightly. The not knowing is especially present here, at the end, and that is all right. The not knowing is not a failure. It is an invitation to rest in the mystery, the way we rested in the mystery of the very beginning. The story comes full circle. It begins in mystery, and it ends in mystery, and in between, there is so much light. The leading theory for the ultimate fate of the universe is something called heat death. The name sounds dramatic, but the reality is anything but. Heat death is not a sudden event. It is not a fire or an explosion or a collapse. It is the slow, gradual, peaceful running down of everything. It is the universe reaching a state of maximum entropy, a state where no more usable energy remains, where no more work can be done, where no more change can occur. It is the final, perfect stillness. Let us explain this in simpler terms. The universe, as we have seen, has been cooling and expanding since the very first moment. Stars form, burn, and die, converting mass into energy, radiating heat and light into space. But every time energy is used, it becomes a little less available for future use. A hot cup of tea cools down. You cannot use the warmth of the tea to do work once it has spread into the room. The energy is still there, in the air molecules moving slightly faster, but it is dispersed, spread out, no longer concentrated. This is the idea of entropy, the measure of how spread out and unavailable energy has become. The total amount of energy in the universe is conserved, but it gradually becomes more and more evenly distributed, less and less able to drive any interesting processes. Heat death is what happens when this process reaches its ultimate conclusion. Every star has burned out. Every white dwarf has cooled to a black dwarf. Every neutron star has stopped spinning. Every black hole has evaporated away into a faint whisper of radiation. Every proton, if they decay, has dissolved into lighter particles. The universe becomes a thin, cold, nearly empty sea of the simplest particles, electrons and neutrinos and photons, spread out across distances that are growing ever larger because of the continued expansion driven by dark energy. The temperature of the universe approaches absolute zero, the coldest possible temperature, where all motion virtually ceases. There are no structures, no objects, no gradients of heat or pressure, no differences at all, just a smooth, uniform, silent vastness. In this state, nothing can happen. There are no events, no changes, no time, in any meaningful sense, because time is measured by change, and there is no change to measure. The universe will have reached a final, perfect equilibrium. It will not be dead, exactly, because death implies the absence of life, and life was only ever a brief flicker. It will simply be a state of pure, unbroken stillness, stretching on forever, or perhaps not forever. If the universe continues to expand, the distances between the remaining particles will grow so large that they will never interact with each other again. Each particle will be alone in its own observable universe, a tiny island of existence in an endless void. And then, perhaps, even the particles themselves will fade, their energy stretched to nothing by the expansion of space. The end, in this picture, is not a bang or a crash. It is a quiet sigh, a final exhale, a soft fading of the last faint light into the dark. But let us step back from this ultimate vision. Let us remember that heat death is a theory, the leading theory, but not the only one. There are other ideas, other possibilities. Some physicists have speculated that the dark energy driving the expansion might not be constant. It might grow stronger over time. If that happens, the expansion could eventually become so powerful that it tears apart galaxies, then stars, then planets, then atoms, then even the fundamental particles themselves. This scenario is sometimes called the Big Rip. It would be a more active end than heat death, but it is less supported by current observations. The data we have right now favors a constant dark energy leading to heat death, but the data is not complete. The universe may still have surprises for us. Another possibility, even more speculative, is that the universe might eventually stop expanding and begin to contract. Gravity, the great gatherer, might eventually overcome the push of dark energy, and the expansion would reverse. The galaxies would come rushing back together. The universe would heat up, compress, and eventually collapse into a hot, dense state, perhaps even a new Big Bang. This is sometimes called the Big Crunch. Some versions of this idea suggest that the universe might then bounce, expanding again, in a cycle of births and deaths that goes on forever. These are beautiful ideas, but they are not yet supported by solid evidence. The current weight of observation leans against them, but the honest truth is that we do not know. The final chapter is still being written, and it may never be fully written within our lifetime, or within the lifetime of our species. And that is all right. The not knowing is part of the piece. The universe does not owe us a definitive ending. It has given us a story, a long and beautiful story, and the fact that the last few pages are still blank is not a flaw. It is a gift. It leaves room for wonder. It leaves room for humility. It leaves room for the quiet acceptance that we are small creatures in a very large cosmos, and that some things will always remain beyond our grasp. Now, as we come to the very end of this telling, let us loop back to where we began. Do you remember? We began with a soft welcome, an invitation to stop trying to picture the whole thing at once, and just follow one moment after another. We began with a number, 13,800,000,000 years, offered gently as something to rest on, not to memorize. We began with permission to drift off at any point, to let the story wash over you without needing to catch every word. And now, here at the end, we return to you, the listener, lying in the dark. You have traveled a long way, from the hot, dense beginning, through the formation of the elements that make up your body, through the birth and death of stars, through the gathering of galaxies, through the formation of your own planet, your own sun, your own home. You have seen the universe at its brightest and at its darkest. You have seen it at its most energetic and at its most still. And through all of it, you have been part of it. The atoms in your body were there, in one form or another, at every stage of the journey. You are not separate from the cosmos. You are the cosmos, briefly awake, briefly aware, briefly telling its own story to itself. And now, as the story comes to an end, you do not need to hold on to any of it. You can let it go. The universe itself is learning to let go, slowly and peacefully, over trillions of years. You can learn to let go too, in this moment, as you drift towards sleep. The story is over. The words are winding down. The voice will soon fall silent, and you will be left with just the quiet, just the dark, just the gentle rhythm of your own breathing. Let that be enough. The universe, in all its vastness, has no more urgent task than simply to be what it is. And you, in this moment, have no more urgent task than simply to be where you are, lying in the dark, warm, still, at peace. The story of everything, from the Big Bang to the final heat death, is a story that contains you, and a story that will one day continue without you. And that is not a sad thing. It is just the way the story goes. Every wave rises and falls. Every breath comes and goes. Every star ignites and fades. And every living being, for a brief and precious moment, gets to be part of it all. So let the story trail off now. Do not look for a conclusion, because there is no conclusion. The universe is still unfolding. The mystery is still mysterious. The quiet is still quiet. And you are still here, still breathing, still resting in the dark. The voice will fall silent, but the quiet will remain. The quiet has always been there, underneath everything, from the very first moment. It was there in the dark ages, when the universe had no stars. It was there in the cold era, when the last stars had gone out. And it is here now, in this room, in this moment, holding you gently as you drift towards sleep. Thank you for listening. Thank you for taking this journey. The universe is vast and old and deeply peaceful, and so are you. Rest now. Let the quiet carry you. There is nothing more to do. There is nowhere else to be. Just this, just here, just the long, quiet end, fading softly into stillness. Good night.